Welcome to Sleepy Science Student, where we explore the cosmos, one gentle thought at a time. Tonight, we're going on a slow, soothing journey into one of the universe's most profound mysteries: what lies on the other side of a black hole? It's a question that touches the very fabric of spacetime, where Einstein's equations whisper secrets about bridges between universes, and where light itself bends in ways that challenge everything we think we know about reality. I hope this video isn't too interesting. Though if it does happen to keep you awake, at least you'll be learning something fascinating about the most mysterious objects in the cosmos. Not the worst way to spend a sleepless night drifting through the event horizons of your imagination. Before we venture toward these cosmic abysses together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this curious little channel grow and means more wonder seekers can find their way here, one peaceful evening at a time. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Melbourne at 2:01 in the morning? Or listening from a quiet corner in Vancouver at 9:00 in the evening while the rain patters softly against your window? Let me know in the comments. It's always such a joy to see this sleepy science community scattered gently across the globe, all of us gazing up at the same mysterious universe. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert or worry about understanding every detail. Just let the words wash over you like starlight filtering through a peaceful night sky. Let your shoulders relax. Let your breathing slow. And as we begin this gentle voyage into the heart of black holes and the mysteries that might lie beyond them, remember this video is for educational and relaxation purposes only. It's not intended as medical advice, astrophysical navigation guidance, or a manual for actual black hole traversal. Though if you do find yourself approaching an event horizon, please reconsider your life choices. Ready? Let's begin. Imagine standing at the edge of existence itself, not metaphorically, but literally, at the boundary where the known universe gives way to something else entirely. This is what a black hole represents. Not simply a massive star that has collapsed, not merely a cosmic vacuum cleaner devouring everything nearby, but a genuine threshold, a doorway where the normal rules of reality stop applying, and something stranger, something we can barely comprehend, takes over. What's on the other side of a black hole? It's one of those questions that sounds simple, almost childlike in its directness, yet contains within it layers upon layers of complexity. To even begin answering it, we need to understand what a black hole really is, how Einstein's beautiful equations describe the warping of space-time around these objects, and what the very concept of other side might mean when space and time themselves become twisted beyond recognition. You might think of a black hole as a kind of hole, naturally enough given the name, but black holes aren't really holes at all, at least not in the way we usually think of them. They're not punctures in the fabric of space, not tears or rips or empty voids. They're more like infinite densities, points where matter has been compressed so thoroughly that it creates a gravitational field so intense that not even light, which travels at the cosmic speed limit of about 300,000 kilometers per second, can escape once it crosses a certain boundary. That boundary has a name that sounds almost poetic: the event horizon. It marks the point of no return, the place where escape velocity equals the speed of light, where the future becomes a one-way street leading inexorably inward. And it's here, at this invisible threshold, where our journey truly begins. Throughout history, humans have wondered about what lies beyond the edges of the known world. Ancient sailors feared falling off the edge of a flat Earth. Early astronomers puzzled over what existed beyond the visible stars. And now, in our modern era, we find ourselves contemplating something far stranger: the possibility that black holes might be portals, gateways, bridges to other regions of space and time, or even to entirely different universes. This isn't science fiction, though it might sound like it. These ideas emerged directly from Einstein's general theory of relativity, published in 1915, which remains our best description of how gravity works. When Einstein's equations are applied to extremely dense objects, they produce solutions that are so bizarre, so counterintuitive, that even Einstein himself struggled to accept them. One of these solutions, worked out by physicist Karl Schwarzschild while serving in the German army during World War I, describes what we now call a black hole. But there's another solution, proposed by Einstein and his colleague Nathan Rosen in 1935, that describes something even stranger: a bridge through space-time connecting two different regions of the universe, or possibly connecting two different universes entirely. This bridge, now known as an Einstein-Rosen bridge, or more commonly as a wormhole, might, just might, be what lies on the other side of a black hole. But we're getting ahead of ourselves. Let's slow down. Let's take this journey one gentle step at a time, beginning where all good stories about black holes begin, with gravity itself. Gravity is the weakest of nature's four fundamental forces, yet it shapes the cosmos on the grandest scales. It's what keeps your feet on the ground right now, what holds the moon in its monthly dance around Earth, what binds our solar system together and sculpts galaxies into their elegant spiral forms. Gravity is also what creates black holes, so understanding gravity is our first step toward understanding what might exist beyond an event horizon. For centuries, people thought of gravity as a force, an invisible pull that massive objects exerted on each other. Isaac Newton described it mathematically in the 1680s with his law of universal gravitation, which worked beautifully for predicting planetary motions and calculating how objects fall. But Newton's gravity had a problem. Though it took more than 2 centuries for anyone to notice, it acted instantaneously across any distance. If the sun suddenly vanished, don't worry, it won't. Newton's equations said Earth would immediately fly off in a straight line, no longer held in orbit. But this created a puzzle. How could Earth instantly know that the sun had disappeared? What carried the information across 150 million kilometers of empty space in 0 time? It seemed to violate the speed limit of the universe that we mentioned earlier. Einstein resolved this puzzle with his general theory of relativity, which reimagined gravity not as a force at all, but as a curvature of space-time itself. This is one of those ideas that sounds simple, but contains profound depths. So let's unpack it slowly and gently. Space-time is the unified fabric of the universe, the arena in which all events occur. Before Einstein, people thought of space and time as separate things. Space was the 3-dimensional stage where events happened, and time was the universal clock that ticked forward at the same rate for everyone. Einstein showed that space and time are actually interwoven into a single 4-dimensional entity. Where you are in space affects how you experience time, and how fast you're moving through space affects how quickly time passes for you. Now, here's where it gets fascinating. In Einstein's vision, massive objects don't pull on other objects through some mysterious force. Instead, they warp the space-time around them, curving it, bending it, creating what you might imagine as a depression or dimple in the fabric of reality. Other objects moving through this curved space-time follow the contours of the curve, which we perceive as gravitational attraction. It's a bit like placing a heavy bowling ball on a stretched rubber sheet. The ball creates a depression, a curve in the sheet, and if you roll a marble across the sheet, it will curve toward the bowling ball. Not because the ball is pulling it with some invisible force, but because the marble is following the curved surface. In space-time, planets orbit stars not because stars pull on them, but because the planets are following the curved space-time created by the star's mass. This might seem like a distinction without a difference, but it's actually profound. Forces can be turned on or off, blocked or shielded against. But you can't block geometry. You can't shield against the curvature of space-time. Gravity, in Einstein's view, is simply the shape of the universe, responding to the presence of matter and energy. And, just as Einstein predicted, gravity doesn't propagate instantaneously. When a massive object moves, it creates ripples in space-time that spread outward at the speed of light. Gravitational waves, which were finally detected directly in 2015, a century after Einstein predicted them. If the Sun vanished, Earth would continue orbiting for about 8 minutes, the time it takes for light, and for gravitational changes, to cross the distance between Sun and Earth. Now, most objects create gentle curves in spacetime. Earth creates a barely noticeable dimple. Even the Sun, which contains 99.8% of all the mass in our solar system, creates only a modest dip. You can escape from the Sun's gravity if you achieve a speed of about 618 kilometers per second. Difficult, but not impossible. We've sent spacecraft to every planet in our solar system and beyond, proving that the Sun's gravitational well can be climbed out of. But imagine compressing all the Sun's mass into a smaller and smaller volume. As the mass gets more concentrated, the curvature of spacetime gets steeper. The depression in the rubber sheet analogy gets deeper. The sides get more vertical. Eventually, if you compress enough mass into a small enough space, the curvature becomes so extreme that it creates what mathematicians call a singularity, a point where the equations of general relativity break down, where density becomes infinite, where space-time curvature becomes infinite. This is a black hole, not a hole in space, but a region where space-time has been curved so severely that it essentially curves back on itself, creating a one-way membrane, the event horizon, beyond which escape is impossible. Let's pause here for a moment. Take a breath. Feel the gentle weight of gravity pressing you into your bed or chair right now. That sensation, so familiar and unremarkable, is the same fundamental phenomenon that creates these cosmic extremes, these regions where the universe becomes strange and mysterious. The event horizon of a black hole is one of the most fascinating boundaries in physics. It's not a physical surface, not a membrane or barrier you could touch. If you were falling toward a black hole and crossed the event horizon, you wouldn't feel anything special at that moment. You wouldn't hit a wall or pass through a shimmering barrier. From your perspective, space would just continue, apparently unchanged. But something profound would have happened. Your future would have changed in an absolute and irrevocable way. Before crossing the event horizon, you could in principle turn around, fire your rockets, and escape back to the wider universe. It would take an enormous amount of energy, and the closer you got to the event horizon, the more energy you'd need, but escape would remain technically possible. After crossing the event horizon, escape becomes not just difficult, but genuinely impossible as traveling backward in time. In fact, that's essentially what you'd need to escape from inside a black hole's event horizon. Travel backward in time. Because inside the event horizon, the roles of space and time become exchanged in a strange and unsettling way. The direction toward the singularity at the black hole's center becomes not a direction in space, but a direction in time, specifically the future. Just as you can't avoid moving forward in time right now, once you're inside a black hole's event horizon, you can't avoid moving toward the singularity. It's not a place you're falling toward anymore. It's a moment in your future, as inevitable as tomorrow. This is one of those concepts that feels impossible to grasp fully, and that's okay. Let it wash over you. We'll return to it. For now, let's think about what observers see when they watch something fall into a black hole. This is where Einstein's relativity produces some genuinely strange effects. Imagine you're watching a clock fall toward a black hole's event horizon. As the clock gets closer and closer, something peculiar happens. It appears to slow down. This isn't an illusion or a trick of perception. Time genuinely runs slower, in stronger gravitational fields, an effect called gravitational time dilation, which has been measured and confirmed countless times. GPS satellites have to account for it to give you accurate directions, running their clocks slightly faster to compensate for Earth's gravity being weaker up in orbit than down on the surface. Near a black hole's event horizon, gravitational time dilation becomes extreme. To you, watching from a safe distance, the falling clock appears to slow down more and more, its ticks growing farther and farther apart. The clock's light also gets stretched to longer and longer wavelengths, shifting toward the red end of the spectrum and eventually becoming invisible as it stretches beyond what our eyes can detect. The clock appears to freeze, hovering forever just above the event horizon, gradually fading from view. But from the clock's perspective, or from the perspective of anything falling into the black hole, time continues normally. The clock crosses the event horizon in a finite amount of its own time, then continues falling toward the singularity. This creates a strange asymmetry. From the outside, nothing ever quite seems to cross the event horizon, while from the perspective of the infalling object, it crosses smoothly and continues onward. Which perspective is right? Both, actually. This is relativity showing us that there's no single, universal time. That time itself is relative, depending on where you are and how you're moving. Now we're beginning to see why asking what's on the other side of a black hole becomes complicated. From an outside perspective, there is no other side. Nothing ever crosses the event horizon. Everything just freezes there forever, fading from view. But from an infalling perspective, there clearly is something beyond the event horizon, more space, more time, leading eventually to the singularity at the center. So which is it? Is there another side or isn't there? The answer depends on your perspective, on your reference frame, on where you are and how you're moving. This is the first hint that black holes challenge not just our intuitions, but our very concepts of here and there, of inside and outside. Let's rest here for a moment. We've covered a lot of ground, from Newton's gravity to Einstein's curved spacetime, from the nature of event horizons to the strange way time behaves near black holes. Before we continue our journey deeper, toward the question of what might lie beyond, take a breath. Let these ideas settle gently in your mind, like snowflakes drifting down on a quiet evening. You don't need to understand every detail. Just let the wonder of it all wash over you. Now, let's talk about bridges. Not the kind that span rivers or connect cities, but bridges through the very fabric of space-time itself. This is where our journey toward understanding what might exist on the other side of a black hole takes a truly remarkable turn, where mathematics reveals possibilities so strange that even their discoverers were skeptical. In 1935, 20 years after Einstein published his general theory of relativity, he was working with a young physicist named Nathan Rosen at the Institute for Advanced Study in Princeton. They were exploring the mathematical solutions to Einstein's field equations, the complex set of equations that describe how matter and energy curve space-time. What they found was unexpected, even to Einstein himself. When they analyzed the geometry of space-time around what we now call a black hole, they discovered something curious embedded in the mathematics. The equations suggested that the extreme curvature of space-time near a black hole didn't just create a one-way trap. Instead, the equations described a kind of tunnel, a bridge connecting two separate regions of space-time. On one end was a black hole, with its event horizon and singularity. On the other end was what they called a white hole, essentially a black hole in reverse, a region where matter and light could only exit, never enter. This Einstein-Rosen bridge, as it came to be known, was a purely mathematical construct at first. It emerged naturally from the equations, but did that mean it existed in reality? Einstein himself was doubtful. The bridge, according to the original calculations, would be extraordinarily unstable. It would form and collapse so quickly that nothing, not even light, could travel through it before it pinched off into nothingness. Imagine trying to run through a tunnel that's collapsing behind you as you go, but where the collapse moves faster than you possibly can. That was the problem with the Einstein-Rosen bridge. It was a theoretical possibility, a mathematical curiosity, but not something that seemed to have any physical relevance. The equations allowed it, but the universe, apparently, did not. Yet the idea wouldn't go away. It lingered in the minds of physicists, this notion that black holes might be connected to something else, somewhere else. And as our understanding of general relativity deepened over the decades, new insights emerged that made the concept of traversable wormholes, another name for these space-time bridges, seem slightly less impossible. Let's slow down and think about what a wormhole actually is, at least in theory. Picture space-time not as a flat, empty stage, but as a flexible fabric that can be bent and warped. Now imagine taking two distant points in this fabric and somehow connecting them with a tunnel, a shortcut through a higher dimension. Instead of traveling the long way across the surface of the fabric, you could dive through the tunnel and emerge far away, having traveled a much shorter distance through a kind of hyperspace. This is the essential idea of a wormhole. It's not just a hole in space, and it's not simply a black hole. It's a hypothetical structure with two mouths, two openings in space-time, connected by a throat, a tunnel through a higher dimension. One mouth might be here, near Earth. The other mouth might be on the far side of the galaxy, or even in another universe entirely. Travel through the throat, and you'd emerge at the other mouth, having bypassed the normal space between them. It sounds like pure fantasy, doesn't it? Like something from a science fiction novel, but it emerges directly from Einstein's equations, which have been tested and confirmed in countless ways over more than a century. The mathematics of general relativity genuinely allows for these structures. Whether the universe actually produces them is another question entirely, one we're still grappling with. One of the physicists who took wormholes seriously was John Archibald Wheeler, who coined the term black hole in 1967. Wheeler was fascinated by the extreme predictions of general relativity, and he explored the mathematics of wormholes extensively in the 1950s and 1960s. He showed that if wormholes existed, they would be governed by the same equations that describe black holes, but with some crucial differences. A black hole has a singularity at its center, a point of infinite density where all the infalling matter accumulates and where the laws of physics as we know them break down. A wormhole, in contrast, wouldn't have a singularity. Instead of crushing everything into infinite density, a wormhole would preserve the shape of the tunnel, allowing matter and light to pass through from one mouth to the other. But there's a catch. Actually, there are several catches, each one more challenging than the last. The first catch is that the equations describing a stable, traversable wormhole require something that has never been observed in nature: exotic matter with negative energy density. Energy density is usually a positive quantity. Matter has positive energy density. Light has positive energy density. Even empty space, according to quantum physics, has a positive energy density due to vacuum fluctuations, tiny temporary particles constantly popping in and out of existence. But a traversable wormhole, according to the equations, needs something with negative energy density to hold the throat open and prevent it from collapsing. Negative energy density sounds like a contradiction, like something that couldn't possibly exist. Energy is energy, right? How can you have negative amounts of it? But quantum mechanics, that other great pillar of modern physics, hints that negative energy might be possible, at least under very special circumstances and in very small amounts. There's a phenomenon called the Casimir effect, discovered in 1948 by Dutch physicist Hendrik Casimir, which produces something resembling negative energy in a tiny gap between two parallel metal plates. The vacuum between the plates has slightly less energy than the vacuum outside, creating a kind of negative pressure that pulls the plates together. This has been measured experimentally. It's real, though the amount of negative energy involved is minuscule. Whether enough exotic matter could exist to stabilize a wormhole large enough for anything to travel through remains an open question. We're talking about theoretical physics at its most speculative here, ideas that are mathematically consistent but far from being established science. And that's perfectly fine. Science advances by exploring possibilities, even ones that seem outlandish. Let's pause again. Take a breath. We've moved from Einstein's curved space-time to the mathematics of wormholes, from the Einstein-Rosen Bridge to exotic matter and negative energy. These are deep waters we're swimming in, and there's no rush to reach the other shore. Just float along gently, letting these fascinating concepts drift around you. Now here's where things get even more interesting, if that's possible. In the 1980s, physicist Kip Thorne, who would later win the Nobel Prize for his work on gravitational waves, was approached by astronomer Carl Sagan, who was writing a science fiction novel called Contact. Sagan wanted to send his protagonist through a black hole to reach a distant star, and he asked Thorne if this made sense scientifically. Thorne pointed out that traveling through a black hole would be fatal. The tidal forces would tear anything apart, and there'd be no way to emerge anywhere. But the question got Thorne thinking seriously about wormholes. Could they be made traversable? Could the equations of general relativity permit a stable tunnel through spacetime that something could actually survive traveling through? Working with his students Michael Morris and Ulvi Yurtseva, Thorne explored the mathematics rigorously. What they found was that yes, in principle, a traversable wormhole was possible within the laws of physics as we understand them. It would require exotic matter to keep the throat open, and it would require very specific configurations, but it wasn't forbidden by general relativity or by quantum mechanics. They published their findings in 1988, and it sparked a renewed interest in wormhole physics. Suddenly, what had been dismissed as a mathematical curiosity became a subject of serious academic research. Papers were published exploring different types of wormholes, different configurations, different possibilities. The field of wormhole physics was born, not as a practical engineering discipline, we're nowhere close to building wormholes, but as a way of testing the limits of our theories and exploring the full range of what the universe might allow. One of the most intriguing possibilities that emerged from this research was that wormholes might not just be shortcuts through space, but also shortcuts through time. A wormhole connects two regions of space-time, remember, not just two regions of space. And because time behaves differently in different gravitational fields, you could imagine creating a wormhole where the two mouths experience time at different rates. Here's how it might work, at least in theory. Suppose you create a wormhole with both mouths initially at the same location, experiencing time at the same rate. Now you take one mouth and accelerate it to nearly the speed of light, then bring it back. According to special relativity, time would pass more slowly for the moving mouth than for the stationary one. This is called time dilation, and it's been measured experimentally with atomic clocks on airplanes and satellites. When you bring the moving mouth back, the two mouths are now at different times. Step through the wormhole in one direction, and you travel forward in time. Step through in the other direction, and you travel backward. You've created a time machine from a wormhole. This raises all sorts of paradoxes, of course. If you could travel backward in time, could you prevent your own birth? Could you change the past? Physicists have spent considerable effort thinking about these paradoxes, and the general consensus is that the universe probably protects itself from such contradictions through various mechanisms. Quantum effects might cause any time machine wormhole to be unstable and collapse. Or perhaps the consistency of history is enforced by the laws of physics in ways we don't yet fully understand. The British physicist Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel and protect causality. It's not proven, but it seems likely that the universe doesn't permit paradoxes. Exactly how it enforces this protection remains one of the delightful mysteries we're still exploring. But let's return to our original question. What's on the other side of a black hole? We've been talking about wormholes as if they're definitely connected to black holes, but the relationship is more subtle than that. A black hole, as it exists in our universe, probably isn't a wormhole. The mathematics that describes real physical black holes, the kind formed from collapsed stars, doesn't include a traversable passage to anywhere else. When a star collapses and forms a black hole, what you get is an event horizon surrounding a singularity. Matter and light can fall in, but they don't emerge somewhere else. They fall toward the singularity and are, as far as we can tell, crushed out of existence, their information scrambled or lost. There's no exit, no white hole at the other end, spitting things back out. The Einstein-Rosen bridge that connects a black hole to a white hole is a solution to Einstein's equations for an eternal black hole, one that has always existed and will always exist, one that formed from unusual initial conditions rather than from a collapsing star. This is called a Schwarzschild wormhole, after Carl Schwarzschild, who first found the solution. But even this idealized wormhole isn't traversable. As we mentioned earlier, it collapses too quickly for anything to get through, so we seem to be at an impasse. Black holes probably aren't wormholes. Wormholes, if they exist, would require exotic matter we've never seen. And even if wormholes could exist, they might be too unstable to use or too small to detect. Is this journey leading nowhere? Not quite. Because there are still deeper questions to explore, still more fascinating possibilities to consider. What we've learned so far is that the equations of general relativity permit structures far stranger than everyday experience would suggest. Black holes exist. We've observed them. We've photographed their shadows. We've detected the gravitational waves they produce when they collide. The universe is already stranger than common sense would allow. And there are hints, tantalizing mathematical hints, that the relationship between black holes and wormholes might be more subtle than we first thought. Some modern theories in quantum gravity suggest that every black hole might be connected to a partner black hole in some other region of space or time, linked by a quantum connection that doesn't allow matter to pass through, but still creates a deep correlation between them. This is getting into very speculative territory, the kind of frontier physics where mathematics runs ahead of experiment and ideas remain tentative, waiting for confirmation or refutation. But that's where the most exciting mysteries live, isn't it? At the edges of knowledge, where questions outnumber answers and wonder outpaces certainty. Let's rest here again. Breathe slowly. We've journeyed through the mathematics of wormholes, through time machines and chronology protection, through the subtle distinctions between real black holes and hypothetical traversable tunnels through space-time. The picture is complex, perhaps frustratingly so, but that complexity is part of what makes black holes so endlessly fascinating. In our next section, we'll explore what actually happens as you fall into a black hole, what the journey toward the singularity might feel like, and what Einstein's equations tell us about the nature of that central point where physics as we know it breaks down. We'll approach the heart of darkness gently, one thought at a time. Let's imagine, just for a moment, that you're falling into a black hole. Not a massive galaxy-sized supermassive black hole, but a stellar mass black hole, the kind that forms when a massive star collapses at the end of its life. This black hole has a mass perhaps 10 times that of our Sun, and its event horizon stretches about 30 kilometers across. You're approaching it in a spacecraft, and for reasons we won't question, you've decided to cross the event horizon and see what lies beyond. What would this journey actually be like? What would you see? What would you feel? And what would ultimately happen to you? These aren't just thought experiments or idle speculation. Einstein's equations allow us to calculate exactly what an infalling observer would experience, at least up until the point where quantum effects become important and our current theories break down. So let's take this journey together, slowly and gently, step by step into the unknown. First, let's establish where you are. You're still outside the event horizon, maybe a few hundred kilometers away, drifting in your spacecraft with the engines off. The black hole itself is invisible against the darkness of space. It emits no light, reflects no light, and appears as a perfectly black sphere. But you can see it by what it does to the space around it. Behind the black hole, there are stars. Thousands of them, scattered across the cosmic background. But as you look at the region around the black hole, something strange happens to those stars. Their light bends as it passes through the curved spacetime near the black hole, creating a gravitational lens. Stars directly behind the black hole appear as a bright ring encircling the darkness, what astronomers call an Einstein ring. Stars to the sides appear distorted, stretched, their positions shifted from where they should be. This is your first direct observation of curved spacetime. Light, which always travels in straight lines through flat space, follows curved paths in the warped geometry around the black hole. The more massive the black hole, the more severe the bending. And what you're seeing is the entire universe behind the black hole, compressed and distorted into patterns around its edge. Now you begin to fall. Perhaps you fire your engines briefly to nudge yourself toward the event horizon, or perhaps you simply let the black hole's gravity pull you in. Either way, you start to accelerate. Slowly at first, then faster and faster as you approach. One of the first things you notice is that the black hole appears to grow. This isn't because it's actually getting bigger, but because more and more of your field of view is taken up by the event horizon and the distorted space around it. The ring of light from background stars grows wider, brighter, more complex. You begin to see multiple images of the same stars as light takes different curved paths around the black hole to reach your eyes. If you look back the way you came, toward the wider universe, something remarkable happens. The stars behind you appear to concentrate into a smaller and smaller region of the sky, clustering toward a single point directly opposite the black hole. This is the flip side of the gravitational lensing, space-time curvature that focuses the entire external universe into your backward view, like looking through the wrong end of a telescope. Colors begin to shift. Light from objects closer to the black hole than you are gets blue-shifted, compressed to shorter wavelengths, because that light is climbing up out of a deeper gravitational well to reach you. Meanwhile, light from the distant universe behind you gets red-shifted, stretched to longer wavelengths. The universe takes on a strange, color-distorted appearance, blues and reds intensifying in different directions. You're falling faster now. The event horizon grows to fill half your field of view, then more. The ring of distorted starlight becomes a bright halo surrounding an expanding darkness. Time, from your perspective, continues to flow normally. Your watch ticks at its usual rate. Your heartbeat remains steady. But you know, because you've studied the mathematics, that to an outside observer, you appear to be slowing down, your image redshifting and freezing just above the event horizon. This creates a strange asymmetry, one worth pondering quietly for a moment. From the outside universe's perspective, you never quite reach the event horizon. You appear to slow down asymptotically, your light getting dimmer and redder until you fade from view altogether over the course of seconds, minutes, or hours, depending on the black hole's mass. To anyone watching from a safe distance, you simply vanish, your last moments stretched out across an infinite amount of their time. But from your perspective, none of this happens. You continue falling at an ever-increasing rate. You feel nothing special. The event horizon approaches in a finite amount of your time, maybe a few seconds for a stellar mass black hole, maybe a few hours for a supermassive one, and then you cross it. The moment of crossing is subtle. There's no physical barrier, no sudden transition, no flash of light or jolt of force. The event horizon is a mathematical surface, not a material one. It's defined purely by geometry, the point where space-time curvature becomes so extreme that all future directed paths lead inward. You cross it smoothly, continuously, perhaps without even noticing the exact moment it happens. But something profound has changed. You are now inside the event horizon, in a region of space-time where escape is no longer possible. And here's where things get truly strange, where our intuitions about space and time completely fail us. Inside the event horizon, the direction toward the singularity, toward the center of the black hole, is no longer a direction in space. It's a direction in time. Specifically, it's the future. Just as you can't avoid moving forward in time right now, sitting or lying wherever you are, you can't avoid moving toward the singularity once you're inside the event horizon. The singularity isn't a place you're falling toward. It's a moment in your future, as inevitable as tomorrow, as unavoidable as death. This is one of those concepts that feels impossible to truly grasp, and that's understandable. Our brains evolved to navigate three-dimensional space, not four-dimensional space-time, and certainly not regions where the roles of space and time become exchanged. Let it be strange. Let it be incomprehensible. Some aspects of reality simply don't map onto human intuition. What you can grasp is what happens next, because it's calculable and concrete, if thoroughly unpleasant. As you continue falling toward the singularity, tidal forces begin to become noticeable. Tidal forces are differences in gravitational pull across an extended object. Your feet, being slightly closer to the singularity than your head, experience slightly stronger gravity. This difference stretches you. For a stellar mass black hole, these tidal forces become severe very quickly. By the time you cross the event horizon, they're already strong enough to be uncomfortable. As you fall deeper, they intensify rapidly, stretching you lengthwise while simultaneously compressing you from the sides. This process has a rather graphic name in the physics literature: spaghettification. It's not a pleasant way to go. The tidal forces would tear you apart long before you reached the singularity, breaking molecular bonds, ripping cells apart, reducing you to a stream of atoms and then subatomic particles, all being pulled inexorably inward. For a stellar mass black hole, this would happen within a fraction of a second after crossing the event horizon. But, and here's a curious detail, the experience would be different for larger black holes. Tidal forces depend not just on the strength of gravity, but on how quickly gravity changes with distance. For a supermassive black hole, the kind that lurks at the center of most galaxies, with a mass millions or billions of times that of the Sun, the event horizon is so large and the curvature so relatively gentle that you could cross it without feeling any significant tidal forces at all. You could, in principle, pass through the event horizon of a supermassive black hole and survive, at least for a while. You'd have hours, maybe days of relatively comfortable existence inside the event horizon before the tidal forces near the singularity became lethal. This is a strange and counterintuitive fact. The bigger the black hole, the gentler its event horizon, the longer you could survive inside. Of course, surviving is relative. You're still doomed. The singularity still lies in your inevitable future. But you'd have time to look around, to observe, to perhaps send signals to any other unfortunate travelers who'd fallen in with you. You couldn't send signals out. Nothing escapes from inside the event horizon, but you could communicate with other infalling observers who were behind you, deeper in the gravitational well. What would you see inside the event horizon? This is harder to answer definitively because it depends on exactly how you're falling and what angle you're looking at. But the mathematics gives us some clues. If you looked outward, back toward the event horizon you'd crossed, you'd see a bright ring of light, the entire external universe visible as an increasingly compressed and blue-shifted circle in the sky. All of cosmic history from your crossing onward would appear to play out in that ring, faster and faster as you fell deeper. This is the time reversal we mentioned earlier manifesting in a visual way. From outside, observers see you slow down and freeze. From inside, you see the outside universe speed up. The asymmetry of perspective is complete and absolute. If you looked inward, toward the singularity, you'd see, well, nobody knows for certain. The singularity is hidden in your future, not visible as a thing in space. You might see other matter that fell in before you, compressed and distorted by the extreme space-time curvature. You might see strange optical effects as light paths become more and more chaotic. Or you might see something else entirely, something that our current theories can't predict. Because here's where we need to be honest about the limits of our understanding. Einstein's general relativity predicts that at the singularity, space-time curvature becomes infinite, density becomes infinite, and the equations themselves break down. They produce infinities, which in physics is usually a sign that the theory is incomplete, that it's being applied beyond its range of validity. Infinities in physics are like error messages. They tell us we've reached the edge of what our current theories can describe, and the singularity at the center of a black hole is almost certainly one of these edges. Most physicists believe that quantum effects, which general relativity doesn't account for, become crucial at the tiny scales and enormous densities near the singularity. We need a theory of quantum gravity, a framework that unifies general relativity with quantum mechanics, to truly understand what happens at a black hole's center. We don't have that theory yet, not a complete one anyway. We have candidates, like string theory and loop quantum gravity, which make different predictions about what replaces the singularity. In some versions of string theory, the singularity is replaced by a high-dimensional structure where space and time behave in radically different ways. In loop quantum gravity, the singularity might be replaced by a bounce, a region where the collapse reverses and matter begins expanding again, possibly into another universe. These are speculative ideas, mathematical explorations of possibility rather than established science. But they share a common theme. The singularity, as described by classical general relativity, probably isn't real. It's a placeholder, a sign that we're missing something important. What actually exists at the center of a black hole remains one of the deepest unsolved mysteries in physics. Let's take a breath here. We've followed the journey inward, from the approach to a black hole through the crossing of the event horizon and down toward the mysterious singularity. It's been an intense voyage, full of strange physics and uncomfortable ends. But it's also been illuminating, showing us how our best theories describe these extreme environments and where those theories reach their limits. Now, you might be wondering, if the singularity is probably not real, if quantum effects replace it with something else, what might that something else be? And could that something else be a connection to another region of space, another universe, another time? Could the other side of a black hole be a quantum realm where the rules change completely? These questions take us into the realm of quantum mechanics and quantum gravity, where the picture becomes even more fascinating and even more uncertain. Some theoretical physicists have proposed that black holes might be connected to white holes through quantum tunnels, or that they might give birth to baby universes that bud off from our own. Others suggest that the information that falls into a black hole isn't destroyed, but is somehow encoded on the event horizon, like a hologram. There's a famous paradox called the black hole information paradox, which asks, what happens to the information contained in matter that falls into a black hole? According to quantum mechanics, information can't be destroyed. It can be scrambled, hidden, transformed, but not erased. But if matter falls into a black hole and is crushed at the singularity, where does its information go? Stephen Hawking spent decades thinking about this paradox. In the 1970s, he discovered that black holes aren't completely black. They emit a faint radiation due to quantum effects near the event horizon, now called Hawking radiation. This radiation carries away energy, causing the black hole to slowly evaporate over unimaginably long timescales. A stellar mass black hole would take longer than the current age of the universe to evaporate completely, but eventually it would vanish. But Hawking radiation, as originally calculated, doesn't carry information about what fell into the black hole. It's random, thermal, like the glow from a hot coal. If the black hole evaporates completely, and all that's left is this random radiation, the information about everything that fell in would be lost, violating quantum mechanics. This is the paradox. Hawking himself went back and forth on how to resolve it. Other physicists proposed various solutions. Some suggested the information is encoded in subtle correlations in the Hawking radiation. Others proposed that it's preserved at the singularity or in some remnant left after evaporation. Still others suggested it might escape through a wormhole to another universe. In 2004, Hawking conceded that he'd been wrong, that information is probably preserved somehow, though exactly how remains unclear. The debate continues, with new papers and new ideas appearing regularly. It's one of the most active areas in theoretical physics, sitting at the intersection of general relativity, quantum mechanics, and thermodynamics. What's relevant for our question, what's on the other side of a black hole, is that many of these proposed solutions involve some kind of connection between the black hole's interior and something else. Maybe another region of spacetime, maybe a quantum information storage system distributed across the event horizon, maybe a network of Planck-scale wormholes foaming through the fabric of space at the tiniest scales. The picture that's emerging from modern theoretical physics is that black holes are far more complex than simple empty voids. They're rich with structure, with quantum information, with connections to the rest of the universe that we're only beginning to understand. The event horizon itself might be a busy place at quantum scales, with virtual particles appearing and disappearing, with quantum entanglement linking particles inside to particles outside, with information encoded in ways we haven't fully deciphered. This brings us to a fascinating recent idea called ER EPR, proposed by physicists Juan Maldacena and Leonard Susskind in 2013. The name comes from combining two famous papers. ER refers to the Einstein-Rosen Bridge paper from 1935, and EPR refers to a paper on quantum entanglement by Einstein, Podolsky, and Rosen from the same year. The ER-EPR conjecture suggests that Einstein-Rosen bridges, wormholes, and quantum entanglement might be the same phenomenon, viewed from different perspectives. Whenever two particles are quantum entangled, sharing correlations that transcend space, they might be connected by a tiny, non-traversable wormhole at the Planck scale. And conversely, the mouths of a wormhole might be quantum entangled with each other. If this idea is correct, and it's very much still a conjecture, not established fact, then black holes would be connected to the rest of the universe through an unimaginably complex network of quantum entanglements and microscopic wormholes. The other side of a black hole wouldn't be a single location, but rather a web of connections threading through the quantum foam of spacetime itself. These are heady ideas, existing at the very frontier of theoretical physics. They're not proven, and they may be wrong or incomplete. But they represent the kind of thinking that modern physics is doing about black holes. Thinking that goes far beyond the classical picture of an event horizon surrounding a singularity. Thinking that tries to account for quantum mechanics and information theory, and the subtle ways that different parts of the universe remain connected, even across apparently impassable barriers. Let's pause once more. Breathe gently. We've traveled from the experience of falling through an event horizon to spaghettification and tidal forces, from the information paradox to Hawking radiation, from classical singularities to quantum connections. The picture has grown richer and more complex, but also more mysterious. And that's appropriate, because black holes are genuinely among the most mysterious objects in the cosmos. What we've learned is that asking, what's on the other side of a black hole, doesn't have a simple answer. The answer depends on what kind of black hole we're talking about, what other side means, and which level of physics we're examining, classical or quantum, theoretical or observational. But we're making progress, both in theory and in observation, and the story continues to unfold. Now let's step back from the theoretical realm, from mathematical wormholes and quantum entanglement, and talk about something wonderfully concrete, what we've actually observed. Because in April 2019, humanity achieved something remarkable. We photographed a black hole. Not an artist's impression, not a computer simulation, but an actual image of light bending around the event horizon of a supermassive black hole at the center of a distant galaxy. This achievement, by the Event Horizon Telescope collaboration, represents one of the most extraordinary technical accomplishments in the history of astronomy. And what it revealed gives us crucial clues about what's happening at the edges of these cosmic abysses, even if it can't tell us directly what lies beyond the event horizon itself. Let's talk about how this was done, because the story is as fascinating as the image itself. You can't simply point a telescope at a black hole and take a picture. Black holes don't emit light, that's the whole point. What you can photograph is the environment around a black hole, particularly the hot, glowing gas that swirls around it as it falls inward. This gas forms what's called an accretion disk, a flattened structure of matter spiraling toward the event horizon like water circling a drain. As gas in the accretion disk spirals inward, friction heats it to extraordinary temperatures, millions of degrees. At these temperatures, the gas glows brilliantly, emitting light across the electromagnetic spectrum from radio waves to X-rays. Some of this light escapes outward, but some of it passes close to the event horizon, where the extreme curvature of spacetime bends its path in dramatic ways. The Event Horizon Telescope isn't a single telescope, but a network of radio telescopes scattered across the globe, from Hawaii to Chile to Antarctica. By combining observations from all these telescopes simultaneously, astronomers created a virtual telescope, effectively the size of Earth itself. The technique is called Very Long Baseline Interferometry, and it achieves angular resolution fine enough to see details the size of a grapefruit on the moon. They needed this extraordinary resolution because even supermassive black holes, with masses millions or billions of times that of the Sun, appear tiny in the sky. The target for the first image was the black hole at the center of the galaxy Messier 87, about 55 million light-years away. This black hole has a mass of 6.5 billion suns and an event horizon about 20 billion kilometers across. Yet from Earth, it appears smaller than an orange on the moon. The team collected data over several nights in April 2017, recording radio waves with a wavelength of 1.3 millimeters. Then came the monumental task of processing the data. Each telescope recorded so much information that it couldn't be transmitted over the internet. The data had to be physically shipped on hard drives to a central facility. Researchers spent 2 years analyzing the observations, calibrating the instruments, accounting for Earth's rotation and atmospheric effects, and using sophisticated algorithms to construct an image from the combined data. And then, on April 10, 2019, they revealed what they'd found: a glowing ring of orange light surrounding a dark center, the shadow of a black hole, the boundary between the knowable universe and the ultimate unknown. Let's look at what this image actually shows, slowly and carefully, because every detail is meaningful. The dark center is the black hole's shadow, a region about 2.5 times the size of the event horizon, where light either falls into the black hole or is bent so severely that it doesn't reach us. This shadow is larger than the event horizon itself because of the extreme light bending near the black hole. Photons that pass within about 1.5 times the event horizon radius get captured or deflected, creating this enlarged shadow. The bright ring around the shadow is called the photon ring. It's formed by light from the accretion disk that has taken various curved paths around the black hole before reaching us. Some of this light comes from the side of the accretion disk that's moving toward us, which appears brighter due to relativistic beaming. Light gets concentrated in the direction of motion when the source is moving at close to light speed. Other light has orbited part way or even fully around the black hole before escaping toward Earth. The ring isn't uniform in brightness. One side appears noticeably brighter than the other. This asymmetry tells us about the black hole's rotation and the disk's orientation. The bright region is where matter in the accretion disk is moving toward us at a significant fraction of light speed. Its light boosted by Doppler shift and relativistic effects. The dimmer region is where matter is moving away from us. What's remarkable is how closely this image matches predictions from general relativity. Researchers had run computer simulations for decades, calculating what a black hole's shadow should look like, given various assumptions about mass, spin, and accretion disk properties. The observed image fits these predictions beautifully, confirming that Einstein's century-old equations accurately describe the behavior of light in these extreme gravitational environments. In 2022, the Event Horizon Telescope collaboration released a second image, this time of the supermassive black hole at the center of our own Milky Way galaxy, called Sagittarius A, pronounced Sagittarius A star. This black hole is much closer, only about 27,000 light-years away, but also much smaller, with a mass of just 4 million suns, compared to M87's 6.5 billion. Despite being closer, it was actually harder to image because the hot gas around it swirls and changes on timescales of minutes, while M87's environment remains relatively stable over hours. The image of Sagittarius A shows a similar structure, a dark shadow surrounded by a bright ring of glowing gas. But because we're looking at it from a different angle and it has different properties, the details differ. The ring appears more face-on, more uniform, with multiple bright spots suggesting clumps of hot gas orbiting the black hole. Again, the observations match theoretical predictions remarkably well. These images are historic, but let's be clear about what they do and don't tell us. They show us the environment immediately around the event horizon, the last photons escaping from just outside the point of no return. They confirm that event horizons exist, that black holes are real, that Einstein's equations work even in these extreme conditions, but they can't show us what's inside the event horizon, because no light comes out from inside. The shadow is opaque, a perfect circle of darkness concealing whatever mysteries lie within. Still, these observations give us powerful indirect evidence about black holes' properties. By measuring the size of the shadow and combining it with other observations of stars and gas orbiting farther out, astronomers can determine the black hole's mass with unprecedented precision. By analyzing the asymmetries in the ring, they can infer the black hole's spin, how fast it's rotating. And here's something fascinating. Black holes can spin, and their spin affects the space-time around them in ways that Einstein's equations predict. A spinning black hole drags space-time along with it, like a marble spinning in honey, drags the honey along. This effect, called frame dragging, creates a region near the event horizon where nothing can remain stationary. Everything must orbit in the same direction as the black hole's rotation. This region is called the ergosphere. The Event Horizon Telescope. Observations of M87 suggest that its black hole is spinning, though measuring the exact spin rate requires careful analysis. The spin has profound implications for the environment around the black hole and for the jets of particles and energy that shoot out from near the black hole at nearly light speed. Jets that can stretch for hundreds of thousands of light years across intergalactic space. These jets are themselves mysterious and remarkable. They're not coming from inside the event horizon. Nothing escapes from there. Instead, they're powered by the intense magnetic fields in the accretion disk and the rotational energy of the black hole itself. Through processes we're still working to fully understand, some of the matter and energy in the disk gets channeled into narrow beams, perpendicular to the disk, shooting out at relativistic speeds. The M87 black hole's jet is particularly impressive, visible in radio images as a bright stream extending about 5,000 light-years from the black hole. It's one of the most energetic phenomena in the universe, carrying the kinetic energy of countless exploding stars concentrated into these narrow beams. And it all originates from the immediate vicinity of the event horizon, from the last stable orbits where matter swirls before plunging inward. Let's pause here and appreciate what we're looking at. These images, these observations, represent light that left the vicinity of these black holes millions of years ago. The light from M87 traveled for 55 million years across intergalactic space before reaching our radio telescopes. It witnessed the curvature of space-time at its most extreme, bent by gravitational fields so powerful that they challenge our comprehension. And now, processed and analyzed, it reveals to us the shape of the unseeable. But there's more that observations can tell us, even if we can't see inside the event horizon. Scientists have detected gravitational waves from merging black holes, ripples in space-time produced when two black holes spiral together and merge into a single, larger black hole. The LIGO and Virgo detectors have observed dozens of these events since the first detection in 2015, and each one provides information about black holes' properties. When black holes merge, they do so in a violent, cataclysmic event that releases more energy in a fraction of a second than all the stars in the observable universe emit in the same time. This energy, is carried away by gravitational waves, by ripples in the fabric of spacetime itself, spreading outward at the speed of light. By detecting and analyzing these waves, scientists can determine the masses and spins of the merging black holes, test whether the merger follows Einstein's predictions, and even search for deviations that might hint at physics beyond general relativity. So far, every gravitational wave observation has matched Einstein's predictions beautifully. The black holes ring down after merging. They oscillate like struck bells, emitting gravitational waves at specific frequencies determined by their mass and spin, exactly as general relativity predicts. If there were something unusual about black holes' interiors, if they had some kind of exotic structure or contained wormholes or white holes, these oscillations might show anomalies. But they don't. The observations are consistent with black holes being exactly what general relativity says they are: regions of extremely curved spacetime with event horizons and, presumably, singularities. This doesn't mean black holes definitely don't contain anything exotic. It just means that if they do, it's hidden behind the event horizon in ways that don't affect the external gravitational field. The event horizon acts as a perfect information barrier, concealing whatever lies within from outside observation. This is both frustrating and fascinating. It means that many questions about black holes' interiors might be fundamentally unanswerable through observation alone. We can theorize, we can calculate, we can propose exotic possibilities, but we can't directly verify them. There's another type of observation that gives us clues about black holes: the motion of stars orbiting around them. At the center of our galaxy, astronomers have tracked individual stars orbiting Sagittarius A for decades. One star, called S2, has an orbital period of just 16 years and comes within about 17 light-hours of the black hole at its closest approach, close enough that relativistic effects become measurable. By carefully tracking S2's motion, astronomers have tested general relativity in the strong field regime. They've observed the precession of its orbit, the way the ellipse rotates slowly over time, which matches Einstein's predictions. They've measured the gravitational redshift of light from the star as it climbs out of the black hole's gravitational well. Every test confirms that general relativity accurately describes the gravitational environment around supermassive black holes. These observations are remarkable achievements, the culmination of decades of patient work tracking stars' positions with extraordinary precision. But again, they tell us about the environment outside the event horizon. The black hole's mass, spin, and gravitational effects are all consistent with Einstein's equations. What lies at the center, whether there's truly a singularity or something more exotic, remains hidden. Let's think about what all these observations collectively tell us. They confirm that black holes exist as real, physical objects, not just mathematical curiosities. They confirm that event horizons exist, that there really are regions of space from which light cannot escape. They confirm that Einstein's general relativity accurately describes the behavior of gravity, light, and matter in these extreme environments. And they show us the magnificent complexity of the regions surrounding black holes: the accretion disks, the jets, the photon, rings, the orbiting stars. But they also show us the limits of what we can observe. The event horizon is a boundary not just in space, but in observability. Beyond it lies a realm we cannot see, cannot measure, cannot directly probe. We can send spacecraft to the outer planets, rovers to Mars, probes into the sun's corona. But we cannot send anything into a black hole and receive data back. The event horizon is a one-way membrane, and information crossing it is lost to us forever. This fundamental limitation means that questions about what's inside black holes, what's at their centers, what's on the other side if there is another side, must be answered through theory and inference rather than direct observation. We must rely on the equations, on the logic of physics, on the search for mathematical consistency. And we must accept a degree of uncertainty that's uncommon in observational science. Yet there's beauty in this limitation, isn't there? In an age where we can image galaxies billions of light years away, where we can detect gravitational waves from the far reaches of the universe, where we can measure the cosmic microwave background from the Big Bang itself, black holes remain genuinely mysterious. They're right there in our galaxy's center, close enough to observe their effects on nearby stars, yet their interiors are utterly inaccessible. They remind us that the universe still holds secrets, that there are still frontiers beyond our reach. The Event Horizon. Telescope continues its work, planning new observations with more telescopes added to the network, hoping to make movies of the material swirling around black holes rather than single snapshots. They want to see the dynamics, the evolution over time, the complex interplay between matter, energy, and curved spacetime. Each new observation will refine our understanding, constrain the theoretical possibilities, bring us incrementally closer to understanding these cosmic enigmas. But will we ever know, with certainty, what's on the other side of a black hole? Will we ever be able to peer past the event horizon and see what lies within? Perhaps not through direct observation. Perhaps the answer will have to come from theory, from finding the right quantum theory of gravity that extends beyond Einstein's classical equations. Or perhaps the question itself will need to be reformulated, reconceived in terms we haven't yet imagined. Let's rest here for a moment. We've journeyed through observational astronomy, through radio interferometry and gravitational wave detection, through the remarkable images of black hole shadows and the patient tracking of orbiting stars. We've seen what science can tell us and where it reaches its observational limits. The picture is both clearer and more mysterious than it was before these observations. Clearer because we've confirmed so much of the theory, more mysterious because we've seen how perfect the concealment is, how absolutely the event horizon hides, what lies beyond. Now let's venture into one of the most peculiar theoretical constructs in all of physics, the white hole. If black holes are regions where nothing can escape, white holes would be their exact opposite, regions where nothing can enter. It's a concept that emerges naturally from Einstein's equations, a mathematical mirror image of black holes, yet one that seems so strange, so divorced from physical reality, that even most physicists consider them to be purely theoretical curiosities, rather than objects that might actually exist in our universe. But let's explore them anyway, slowly and gently, because thinking about white holes illuminates something profound about the nature of time, symmetry, and the laws of physics. And it brings us back to our original question in an unexpected way. If there were white holes, could they be what's on the other side of black holes? The story of white holes begins with symmetry. Physics has a deep relationship with symmetry. In fact, many of the fundamental laws of physics are expressions of underlying symmetries in nature. One of the most basic symmetries is time reversal symmetry. Most fundamental physical laws work exactly the same way, whether time flows forward or backward. If you filmed a collision between two billiard balls and played the video in reverse, the reversed motion would still obey the laws of physics perfectly. Einstein's equations of general relativity also have time reversal symmetry. If you have a solution to Einstein's equations that describes how matter and space-time evolve forward in time, you can reverse the time direction and get another valid solution. Take a black hole solution and reverse time, and you get something that behaves like a black hole running backward, a white hole. Let's think carefully about what this means. A black hole forms when matter collapses inward, creating an event horizon that grows as more matter falls in. Run this backward in time, and you'd see matter exploding outward from a central point, with the event horizon shrinking as matter escapes. This is a white hole, a region where matter and energy fountain outward, where the event horizon is a boundary that can be crossed only from inside to outside, never from outside to inside. In a sense, a white hole is like a black hole's time-reversed twin. Where a black hole has a singularity in your future if you fall in, a white hole would have a singularity in your past if you approach it. Where nothing can escape from a black hole's interior, nothing can enter a white hole's interior. They're mathematical opposites, mirror images in time. The Einstein-Rosen bridge we discussed earlier, the wormhole solution that Einstein and Rosen discovered, actually connects a black hole to a white hole. In the original mathematical solution, spacetime forms a bridge with two mouths. One mouth is a black hole where matter can enter but not exit, and the other mouth is a white hole where matter can exit but not enter. The bridge between them is the throat, the tunnel through spacetime connecting these two regions. This sounds like it might be exactly what we're looking for. The black hole's other side is a white hole, and the two are connected by a traversable tunnel. But remember what we learned earlier. This bridge collapses too quickly for anything to traverse it. And there's another problem, one that becomes apparent when we think about what white holes would actually mean for the universe. If white holes existed and spewed matter outward into the universe, we'd expect to see them. They'd be brilliant beacons, fountains of energy and matter erupting from points in space. Matter emerging from a white hole would be hot, energetic, radiating across the electromagnetic spectrum. Yet we don't see anything in the universe that resembles this description. No mysterious sources of matter appearing from nowhere. No regions where the usual laws of thermodynamics seem reversed. This is the fundamental problem with white holes. They seem to violate the arrow of time, the observed fact that entropy increases and disorder grows as time moves forward. A white hole would be a region of decreasing entropy, of order emerging from chaos, of matter spontaneously organizing itself and flowing outward. While this isn't forbidden by Einstein's equations, which are time-symmetric, it seems deeply incompatible with thermodynamics and with everything we observe about how time actually flows in our universe. There's a famous thought experiment that illustrates this problem. Imagine a white hole existing somewhere in the universe. It can't have matter fall into it from outside. That's forbidden by its event horizon. But what about light and gravitational waves passing by it? In principle, these could interact with the white hole in ways that would let them enter. But if anything enters, even just a single photon of light, the white hole would stop being a white hole. Its time-reversed event horizon would break down, and it would effectively become a black hole. This suggests that white holes, if they could form, would be incredibly unstable. The slightest perturbation from the outside universe would destroy them, converting them into black holes. And since our universe is full of light and particles constantly zipping around, any white hole would almost instantly cease to exist. It's a bit like trying to maintain a perfectly clean room in a house full of cats. Theoretically possible, but practically impossible. Some physicists have proposed that white holes might have existed in the very early universe, shortly after the Big Bang, when the symmetry of physical laws might have allowed them to form. In those first moments, when the universe was extraordinarily hot and dense and expanding rapidly, perhaps white holes could have existed briefly before being destroyed or converting into black holes. But even if this happened, it would have been so long ago, nearly 14 billion years, that no observable traces would remain today. Let's slow down here and consider another possibility, one that's even more speculative but fascinating. Some researchers have suggested that the Big Bang itself might have been a white hole, a moment when matter and energy exploded outward from a singularity in the past, creating the expanding universe we inhabit. This would make the entire universe, in some sense, the inside of a white hole, with the Big Bang singularity playing the role of the white hole's central singularity. It's a poetic idea, and it has a certain symmetry to it. If black holes are places where matter falls inward to a singularity in the future, perhaps white holes are places where matter emerges outward from a singularity in the past. And perhaps our universe's origin fits this pattern. But this is highly speculative, and most cosmologists don't take it literally. The Big Bang and white holes might share some mathematical similarities, but they're not really the same thing. There's yet another intriguing possibility that's been explored in recent years. Perhaps black holes don't exist forever. Perhaps, after an extraordinarily long time, far longer than the current age of the universe, black holes might transform into white holes through quantum effects. This idea comes from loop quantum gravity, one of the candidate theories for quantum gravity we mentioned earlier. In this scenario, matter falling into a black hole doesn't quite reach a singularity. Instead, quantum effects at tiny scales create a kind of quantum bounce. The collapse reverses, and the black hole's interior begins expanding again. But because of the extreme time dilation near the event horizon, this reversal takes an enormous amount of time, as seen from outside. Potentially trillions upon trillions of years. Eventually, though, the black hole would explode outward, becoming a white hole that spews out the matter and energy that had fallen in. If this is true, and it's a big if, then every black hole is potentially a white hole in waiting, a time capsule that will eventually open and release its contents back into the universe. The other side of a black hole would be a future epoch, unimaginably distant, when the black hole has quantum bounced and become white. It's a mind-bending thought, mixing the extreme future with the deep past, suggesting that black holes might be temporal bridges rather than spatial ones. But let's be clear about the status of these ideas. They're theoretical explorations, mathematical possibilities emerging from attempts to extend Einstein's classical equations into the quantum realm. They haven't been confirmed observationally, and they may never be. The timescales involved, if black holes do eventually become white holes, are so vast that we couldn't possibly observe the transition. A stellar mass black hole would take something like 10–100 years to evaporate through Hawking radiation, and the quantum bounce, if it happens, would occur on similar or even longer timescales. That's a number so large it's almost meaningless. For context, the universe is currently about 13.8 billion years old, which is roughly 10 years. The timescale for black holes to become white holes would be longer than the current age of the universe by a factor of 10 to 90, a 1 followed by 90 zeros. The universe would have to age trillions of times its current age before this hypothetical transition could occur. Let's pause and take a gentle breath. We've been exploring white holes, these mathematical mirrors of black holes, these theoretical objects that emerge from time-reversing Einstein's equations but seem incompatible with the universe as we observe it. We've considered whether they could be what's on the other side of black holes, whether the Einstein-Rosen Bridge really connects black and white holes, and whether black holes might eventually become white holes through quantum effects in the unimaginably distant future. The picture that emerges is one of deep uncertainty mixed with mathematical beauty. The equations allow for white holes, but reality seems to forbid them, or at least makes them so unstable or so delayed that they have no observable consequences in our current universe. This is actually a common situation in theoretical physics. Mathematics is more permissive than nature. Not everything that's mathematically possible is physically real. Yet thinking about white holes teaches us something important about time. We experience time as having a direction, an arrow pointing from past to future. Eggs break, but don't spontaneously reassemble. Milk mixes into coffee, but doesn't unmix. Heat flows from hot to cold, but not the reverse. This arrow of time is encoded in the second law of thermodynamics, which says that entropy, roughly speaking, disorder, always increases in isolated systems. Black holes fit naturally with this arrow of time. They represent the ultimate increase in entropy, the ultimate disorder, where information and structure fall inward and are lost or scrambled. White holes would represent time flowing backward, entropy decreasing, order emerging from chaos. And this is why they seem so unphysical, so divorced from reality, because they point the wrong way in time. But here's something curious. At the level of fundamental physics, at the level of individual particles and quantum fields, time reversal symmetry is nearly perfect. If you could watch a single electron interact with a single photon and played the interaction backward, it would look just as physically reasonable. The arrow of time emerges not from fundamental laws, but from statistics, from the fact that there are vastly more disordered states than ordered ones, making the progression from order to disorder overwhelmingly likely. This raises a subtle question. If fundamental laws are time-symmetric, why does time have an arrow at all? Why did the universe begin in a low-entropy state, the hot, dense, smooth Big Bang, and progress toward higher and higher entropy? This is called the past hypothesis, the assumption that the universe's entropy was low at the beginning, and it's one of the deepest mysteries in cosmology. White holes trouble us because they seem to violate this past hypothesis. They would be pockets of decreasing entropy, islands where time flows backward. But perhaps what they really do is highlight how strange and contingent the arrow of time actually is. Time's direction isn't built into the fundamental laws, it's a consequence of boundary conditions, of the particular way our universe began. Some physicists have speculated about universes with different boundary conditions, universes where time might flow differently, or where the past and future are more symmetric. In such universes, white holes might be as common as black holes. But that's not the universe we inhabit. We live in a universe with a strong thermodynamic arrow of time, pointing from a low-entropy past toward a high-entropy future. And in such a universe, white holes seem out of place. There's one more fascinating angle to consider: the relationship between white holes and the beginning of the universe. We said earlier that the Big Bang might resemble a white hole, a moment when matter exploded outward from a singularity. But there's a more subtle version of this idea that's worth contemplating. Some cosmologists have proposed that our universe might have bounced from a previous contracting phase. Instead of beginning from a true singularity, perhaps the Big Bang was actually a big bounce, a moment when a collapsing universe reached a minimum size and then rebounded, beginning the expansion we observe today. In this scenario, the bounce point might have some white hole-like properties, with matter and energy being expelled outward from a highly compressed state. This is related to cyclic cosmology, the idea that the universe might undergo repeated cycles of expansion and contraction, bangs and bounces, stretching across eternity in both directions of time. If true, it would mean that our universe's arrow of time is local rather than absolute, that entropy increases in our current cycle, but might have been decreasing in a previous contracting phase. White holes in this view might be mini bounces, localized reversals of gravitational collapse. These ideas remain highly speculative, on the cutting edge of theoretical cosmology. They're attempts to extend our theories beyond the observational evidence, to explore what's mathematically possible, even if it's not yet, or maybe never, confirmable through observation. This is how physics progresses at the frontiers, by imagining possibilities, working out their implications, and seeing whether they're consistent with what we know and whether they make predictions we can eventually test. So where does this leave us with regard to white holes and the question of what's on the other side of a black hole? The answer seems to be that while Einstein's equations formally allow a black hole to connect to a white hole through an Einstein-Rosen bridge, this connection is likely not traversable, not stable, and possibly not physically real. White holes, if they exist at all, are probably relics of the very early universe, or futures so distant they're effectively forever away. The other side of a black hole, if there is one in the sense of a white hole, is either in the past, a time before our current cosmic epoch, or in the unimaginably distant future when quantum effects might reverse black holes' collapse. Either way, it's not accessible to us here and now. The white hole, if it exists, is separated from the black hole not just by space, but by time, by the fundamental arrow that gives our universe its structure and direction. Let's rest here, at this curious intersection of time, entropy, and theoretical possibility. We've explored the mirror image of black holes, these white fountains that mathematics allows, but nature seems to forbid. We've seen how they challenge our understanding of time's arrow, and how they might connect, tenuously and abstractly, to black holes through wormhole bridges that exist in equations, but perhaps not in reality. The journey continues, though, because there are other possibilities to explore, other ways to think about what might exist on a black hole's far side. The universe is not obligated to match our preconceptions, And the most interesting answers often come from unexpected directions. Let's talk about one of the most beautiful and unexpected discoveries in theoretical physics: black holes glow. This statement would have seemed absurd to physicists before 1974. Black holes, by definition, allow nothing to escape, not matter, not light, not information. They're the ultimate cosmic traps, perfect absorbers that give nothing back. Yet Stephen Hawking showed, through an elegant combination of quantum mechanics and general relativity, that black holes aren't quite as black as their name suggests. This discovery, Hawking radiation, as it came to be known, fundamentally changed our understanding of black holes. It revealed that black holes have temperature, that they emit particles, and that they gradually evaporate over time. And it created one of the deepest paradoxes in modern physics, a puzzle that connects directly to our question about what's on the other side of a black hole, because it forces us to ask, what happens to everything that falls in when the black hole finally disappears? Let's begin gently with the idea behind Hawking radiation. It emerges from a strange feature of quantum mechanics. Empty space isn't actually empty. At the quantum level, space is seething with activity. Pairs of particles and antiparticles constantly pop into existence out of the quantum vacuum, exist for an incredibly brief moment, and then annihilate each other, disappearing back into nothingness. These are called virtual particles, and while they exist for such a short time that they can't be directly observed, their effects can be measured and have been confirmed in numerous experiments. Normally, these virtual particle pairs appear and disappear without leaving any lasting trace. The universe's energy balance remains unchanged. The positive energy of one particle is exactly cancelled by the negative energy of its antiparticle partner. But near a black hole's event horizon, something remarkable can happen. If a virtual particle pair appears right at the edge of the event horizon, one particle might fall into the black hole while the other escapes to infinity. When this happens, the particle that escapes becomes real. It carries away energy into the wider universe. But energy is conserved, so where does this energy come from? It must come from the black hole itself. The black hole loses a tiny amount of mass energy every time this process occurs. Slowly, gradually, over unimaginable spans of time, the black hole radiates energy away and shrinks. This is Hawking radiation, a quantum effect at the event horizon that causes black holes to emit particles and slowly evaporate. The radiation has a thermal spectrum. It looks like the glow from a hot object, with a temperature that depends on the black hole's mass. Smaller black holes are hotter, larger ones are cooler. A stellar mass black hole has a temperature of only about a millionth of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills space. But a tiny black hole, if one existed, would be much hotter and would evaporate much more quickly. Let's think about the temperature for a moment, because it tells us something profound. Temperature, in physics, is related to the average energy of particles. Hot objects have fast-moving particles. Cold objects have slow-moving particles. But what does it mean for a black hole to have a temperature? A black hole is a region of curved spacetime, not a collection of particles. How can geometry have temperature? The answer reveals a deep connection between thermodynamics, quantum mechanics, and gravity. Temperature isn't just about particle motion, it's fundamentally about information and entropy. A system has entropy when there are many different microscopic states that look the same macroscopically. When you know a system's entropy, you can calculate its temperature. And black holes, it turns out, have enormous entropy. In 1972, physicist Jacob Bekenstein proposed that black holes have entropy proportional to the area of their event horizon. This was a radical suggestion at the time. Entropy had always been associated with the number of possible arrangements of particles in a system, but a black hole is featureless. It's completely described by just mass, spin, and electric charge. How could it have entropy? Bekenstein argued that the entropy must be related to the information about all the matter that fell into the black hole, information that's now hidden behind the event horizon. The event horizon's area measures, in some sense, how much information is concealed inside, and if black holes have entropy, then by the laws of thermodynamics, they must also have temperature. Hawking's calculation 2 years later confirmed this, providing the exact relationship between a black hole's mass and its temperature. This connection between area, entropy, and temperature is called black hole thermodynamics, and it's one of the most beautiful syntheses in modern physics. It suggests that there's something deeply fundamental about the event horizon, that it's not just a mathematical surface, but something with physical properties, temperature, entropy, and by implication, information content. But now comes the paradox, the puzzle that has occupied physicists for nearly 50 years. If black holes emit Hawking radiation and gradually evaporate, what happens to all the information about the matter that fell in? Does it emerge somehow encoded in the radiation? Or is it lost forever when the black hole finally evaporates completely? Let's explore why this is such a profound question. In quantum mechanics, information is never destroyed. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any future time. The evolution is deterministic and reversible. Like a movie, you can run forward or backward. This principle, called unitarity, is fundamental to quantum mechanics. Without it, probability wouldn't be conserved and the theory wouldn't work. But Hawking's original calculation suggested that the radiation coming from a black hole is completely thermal, completely random. It carries no information about what fell in. Imagine throwing a book into a black hole with all its words and information. According to Hawking's calculation, what comes out is just random thermal radiation, like the glow from a hot coal. The information in the book would be destroyed, violating quantum mechanics' fundamental principle. This is the black hole information paradox. Either information is destroyed when black holes evaporate, violating quantum mechanics, or somehow the information escapes, which seems impossible since nothing can escape from inside the event horizon. Both options seem unacceptable, yet one of them must be true, or our understanding of physics is incomplete in some fundamental way. Hawking himself initially believed that information was destroyed, that black holes were the one exception to quantum mechanics rules. This was a radical position, and it sparked heated debates throughout the physics community. Other physicists argued that information must be preserved somehow, that the Hawking radiation must carry subtle correlations encoding everything that fell in, even if we can't detect these correlations with current technology. The debate reached its peak in the 1990s and early 2000s, with prominent physicists on different sides. Leonard Susskind, a theoretical physicist at Stanford, became one of the leading advocates for information preservation. He and Hawking had a famous bet on the question, a friendly wager that symbolized the deep uncertainty in the field. The stakes were modest, an encyclopedia from which information could be recovered, but the implications were profound. In 2004, Hawking conceded the bet. He announced at a conference that he'd changed his mind. That information probably is preserved after all. But he was vague about the mechanism. How exactly the information escapes remained unclear. The concession didn't end the debate. It just shifted it to the question of how information gets out, rather than whether it does. Let's pause here and breathe slowly. We're in deep conceptual waters, swimming through paradoxes that touch the very foundations of physics. The black hole information paradox isn't just a puzzle about black holes. It's a challenge to our understanding of how quantum mechanics and gravity fit together. Take your time with these ideas. Let them settle gently. One of the proposed solutions to the information paradox is that information is encoded on the event horizon itself rather than inside the black hole. This idea is called the holographic principle, and it suggests something truly remarkable, that all the information about a three-dimensional volume of space can. Let's turn now to one of the most remarkable discoveries in theoretical physics, one that fundamentally changed how we think about black holes and raised profound questions about what happens to information, matter, and energy that falls past the event horizon. This discovery is Hawking radiation, named after Stephen Hawking, who predicted it in 1974 through a brilliant synthesis of quantum mechanics, general relativity, and thermodynamics. Before Hawking's work, black holes were thought to be truly black, perfect absorbers that took in everything and emitted nothing. Once something crossed the event horizon, it was gone forever, adding to the black hole's mass, but otherwise leaving no trace. Black holes would grow over time as they consumed matter and energy, becoming larger and more massive, existing eternally as cosmic traps from which nothing could escape. But Hawking showed that this picture wasn't quite right. When you account for quantum mechanics, the physics of the very small, where particles behave in strange and probabilistic ways, black holes aren't completely black after all. They emit a faint glow, a thermal radiation that carries energy away from the black hole, causing it to slowly lose mass over time. Eventually, over timescales so vast they make the current age of the universe seem like an eye blink. A black hole will evaporate completely, vanishing in a final burst of radiation. Let's explore how this works, gently and carefully, because it involves some of the most subtle and beautiful physics ever discovered. We'll need to talk about quantum vacuum fluctuations, about particle-antiparticle pairs, and about how the extreme environment near an event horizon can turn virtual particles into real ones. It's strange territory, but we'll navigate it slowly, one concept at a time. First, let's talk about empty space, about what we call the vacuum. You might think of empty space as truly empty, containing nothing at all, but quantum mechanics tells us that's not quite right. Even in the emptiest possible space, far from any matter or energy, the vacuum is actually seething with activity at the smallest scales. Quantum fields pervade all of space, and these fields are subject to quantum uncertainty. They fluctuate randomly, creating temporary pairs of particles and antiparticles that pop into existence and then annihilate each other almost immediately. These are called virtual particles, and they exist for such brief moments that they don't violate conservation of energy. They borrow energy from the quantum vacuum and pay it back before anyone can notice, so to speak. This might sound like a mathematical fiction, but virtual particles have real, measurable effects. They contribute to the Casimir effect we mentioned earlier, and they affect the energy levels of atoms in ways that have been measured with extraordinary precision. Now imagine what happens when this quantum vacuum exists near the event horizon of a black hole. The vacuum fluctuations continue, pairs of virtual particles constantly appearing and disappearing. But occasionally, a pair appears right at the event horizon, with one particle just inside and one particle just outside. When this happens, something remarkable occurs. The pair can't recombine and annihilate because one particle is trapped behind the event horizon while the other is free to escape. The particle outside the event horizon becomes real, flying away from the black hole as genuine radiation. The particle inside the event horizon falls toward the singularity. But here's the crucial detail. The particle that fell in has negative energy relative to the outside universe. From the black hole's perspective, it has lost a tiny bit of mass energy. The escaping particle carries away positive energy, and the black hole shrinks by a corresponding amount. This is Hawking radiation. The black hole appears to glow with a faint thermal radiation, as if it had a temperature. And indeed, Hawking showed that black holes do have a temperature, one that's inversely proportional to their mass. The more massive the black hole, the lower its temperature. A stellar mass black hole has a temperature just a tiny fraction of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. A supermassive black hole would be even colder. This means that right now, stellar mass black holes are actually absorbing more energy from the cosmic microwave background than they emit through Hawking radiation. They're growing, not shrinking. Only when the universe has expanded and cooled sufficiently, only after another few trillion years, will the cosmic microwave background temperature drop below black holes' Hawking temperature, and only then will they begin to lose mass. But eventually, they will evaporate. As a black hole loses mass through Hawking radiation, its temperature increases. It gets hotter, radiates faster, loses mass more quickly, gets hotter still. It's a runaway process. A stellar mass black hole would take something like 10 to 67 years to evaporate completely, a number so large it's hard to even conceptualize. For comparison, the universe is currently only about 10 to 10 years old. We're talking about timescales longer than the age of the universe by a factor of more than a trillion. Still, the principle is there. Black holes are not eternal. Given enough time, they will evaporate, shrink, and eventually vanish in a final burst of high-energy radiation. This changes the entire conceptual landscape around black holes. They're no longer permanent features of the universe, but temporary ones, transient structures that exist for a while and then fade away. Let's pause here for a moment. Take a breath. We've introduced some complex ideas: virtual particles, quantum vacuum fluctuations, negative energy particles, thermal radiation from black holes. These concepts stretch our intuitions, challenge our everyday understanding of how reality works. That's okay. Let them settle gently in your mind, like snow falling on a winter evening. You don't need to grasp every detail perfectly. Just let the wonder of it wash over you. Now, here's where things get even more interesting, where Hawking radiation leads us into one of the deepest puzzles in modern physics, the black hole information paradox. This paradox asks a simple question with profound implications. What happens to information that falls into a black hole? In quantum mechanics, information is a fundamental quantity. Every particle, every quantum state carries information about its position, momentum, spin, and other properties. And according to the laws of quantum mechanics, information cannot be destroyed. It can be transformed, scrambled, hidden in complex correlations, but the total amount of information in the universe remains constant. This is called unitarity, and it's a cornerstone of quantum theory. But what happens when you drop a book into a black hole? The book contains information: the arrangement of atoms, the words on the pages, the particular quantum state of every particle. That information crosses the event horizon and falls toward the singularity. From an outside perspective, is that information destroyed? Has it been removed from the universe? For decades, physicists thought the answer was yes, or at least the information was irretrievably hidden behind the event horizon, which amounts to the same thing practically. But then Hawking radiation complicated the picture. If black holes evaporate, if they eventually vanish completely, what happens to all the information that fell into them? Hawking radiation, as originally calculated, is purely thermal. It's random, like the glow from a hot coal, carrying no information about what fell into the black hole. If a black hole evaporates through Hawking radiation, and all that's left is this random thermal radiation, the information about everything that fell in, the book, the stars, the planets, every atom and photon, would be lost forever. This would violate quantum mechanics' fundamental principle of unitarity. This is the information paradox. Black holes seem to destroy information, but quantum mechanics says information can't be destroyed. One of these principles must be wrong, or our understanding is incomplete. Stephen Hawking himself argued for years that information really is destroyed in black holes, that quantum mechanics needs to be modified to allow for information loss. Many other physicists disagreed, arguing that somehow, some way, the information must be preserved. The debate raged for decades, generating countless papers, conferences, and even famous bets between prominent physicists. In 2004, Hawking conceded a bet he'd made with physicist John Preskill, admitting that he'd been wrong, that information probably is preserved somehow. But exactly how it's preserved remains an open question. one that researchers are still actively working on. There are several proposed solutions to the information paradox, each involving different mechanisms and making different assumptions about quantum gravity. Let's explore a few of them gently, seeing how they try to resolve this deep puzzle. One possibility is that information is encoded in subtle correlations in the Hawking radiation itself. Maybe the radiation isn't purely thermal after all. Maybe it carries information in ways too subtle for Hawking's original calculation to capture, requiring a more complete understanding of quantum gravity to see. As a black hole evaporates, it might release information gradually through these correlations, like a book being burned page by page, with the information preserved in the pattern of smoke and ash. This would mean that if you could collect all the Hawking radiation from an evaporating black hole and analyze it with perfect precision, accounting for every quantum correlation, you could, in principle, reconstruct everything that fell in. The information wouldn't be lost. It would just be scrambled in an extraordinarily complex way. This is currently the most widely accepted resolution to the paradox, though the details of exactly how information gets encoded in the radiation remain unclear. Another possibility involves the event horizon itself. Some researchers have proposed that information isn't really destroyed, but is somehow stored on the event horizon, encoded in quantum properties of the horizon's surface. This idea is related to something called the holographic principle, which suggests that all the information in a volume of space can be encoded on the boundary of that region, like a three-dimensional image encoded in a two-dimensional hologram. If the holographic principle applies to black holes, then the event horizon acts as a kind of information storage system, a quantum hard drive where everything that falls in is recorded. As the black hole evaporates, this information would be gradually transferred to the outgoing Hawking radiation. The black hole's interior might not even contain as much information as we'd think. The real information content might live on the boundary, on the event horizon itself. This is a radical idea, suggesting that our three-dimensional world might in some sense be a projection from a two-dimensional surface. But it's taken seriously by many theoretical physicists, because it emerges naturally from string theory and other approaches to quantum gravity. If true, it would mean that asking what's inside a black hole might be the wrong question. The inside and the boundary might be different descriptions of the same physical reality. A third possibility, more speculative but fascinating, is that information doesn't escape through Hawking radiation at all, but instead passes through to another region of spacetime, perhaps through a wormhole, perhaps into a baby universe that buds off from our own. In this scenario, information isn't destroyed and doesn't need to escape through radiation. It simply continues existing somewhere else, in another branch of reality inaccessible to outside observers. This brings us back to our original question about what's on the other side of a black hole. If information that falls in doesn't come back out through Hawking radiation, if it can't be destroyed, then where does it go? Maybe it really does pass through to something else, not a classical wormhole to another location in our universe, but a quantum connection to another universe entirely, or to a region of space-time that branches off from ours. These baby universe scenarios are highly speculative, existing at the very edge of theoretical physics. They emerge from certain approaches to quantum gravity, but haven't been observationally confirmed, and may never be. Still, they represent one possible answer to both the information paradox and the question of what's beyond the event horizon. Another universe, a pocket of space and time that separated from ours when the black hole formed, carrying information with it into a separate realm. Let's take another gentle pause here. Breathe slowly. We've moved from Hawking radiation to quantum information, from the evaporation of black holes to the paradox of where information goes, from holographic horizons to baby universes. These are deep waters, philosophical as much as physical, touching on the nature of reality itself. Feel free to let these ideas float through your consciousness without grasping too tightly at any particular one. There's another fascinating aspect of Hawking radiation worth contemplating. What happens at the very end of a black hole's evaporation? As the black hole shrinks and its Hawking temperature rises, it radiates faster and faster. Eventually, when it's down to roughly the Planck mass, about 22 micrograms, or the mass of a large bacterium, it would be radiating at an extraordinary rate, its temperature reaching something like 10^32 Kelvin. What happens next is unclear. Does the black hole vanish completely in a final explosion of radiation? Does it leave behind a remnant, a stable nugget of Planck-scale quantum gravity that persists? Or does something else happen, something our current theories can't predict? This is the Planck scale, the realm where quantum mechanics and gravity become equally important, where spacetime itself becomes grainy and uncertain, where our current theories reach their limits. Some physicists have suggested that these Planck-scale remnants might persist indefinitely, containing all the information that fell into the black hole compressed into a quantum state we can't currently describe. There would be enormous numbers of these remnants scattered through the universe, invisible and inert, each one a time capsule preserving information from black holes long vanished. It's an eerie thought that the universe might be filled with these quantum ghosts, remnants of gravitational collapse from the distant past. Others argue that remnants are unlikely, that they would violate various principles or lead to contradictions. The debate continues, unresolved, because we simply don't have a complete theory of quantum gravity to settle the question. This is one of those places where theoretical physics is genuinely stuck, waiting for new mathematical insights or new observational clues to point the way forward. Hawking radiation has never been directly observed. The temperature of stellar mass black holes is so low and the radiation so faint that it's completely swamped by other sources of radiation in the universe. We can't point a telescope at a black hole and measure its Hawking glow. But the theoretical prediction is robust, emerging naturally when you combine quantum field theory and curved spacetime with Einstein's equations. Most physicists are confident that Hawking radiation is real, even though we can't yet detect it. There have been analog experiments, though, that demonstrate similar physics in different systems. Researchers have created sonic black holes in flowing fluids, regions where the fluid flows faster than sound waves can propagate, creating an acoustic event horizon. These sonic black holes emit a Hawking-like radiation of phonons, sound wave quanta, that matches the theoretical predictions. Similar experiments have been done with light in optical fibers and with quantum gases. While these aren't real black holes, they demonstrate that the basic mechanism Hawking identified is real and observable in analog systems. Still, it would be wonderful to someday detect actual Hawking radiation from an astrophysical black hole. It would confirm one of the most beautiful theoretical predictions in physics and give us direct observational access to quantum effects in curved spacetime. But given the faintness of the signal, this may remain beyond our technological reach for a very long time, perhaps forever for stellar mass black holes. There is one scenario where Hawking radiation might be observable, if microscopic black holes exist. Some theories predict that black holes much smaller than stellar masses could be created in high-energy particle collisions, or could have formed in the very early universe. These primordial black holes, if they exist with masses below about 10 or 15 grams, would be evaporating right now, their Hawking temperature high enough to radiate noticeably. Researchers have searched for evidence of evaporating primordial black holes by looking for distinctive patterns in cosmic rays and gamma rays. So far, none have been found, which places limits on how many such black holes could exist. But the searches continue, and finding one would be revolutionary. Direct evidence of Hawking radiation, proof that black holes evaporate, and a window into physics at scales far beyond what particle accelerators can reach. The deeper you go into Hawking radiation and the information paradox, the more you realize how much we still don't understand about black holes. They're not simple objects, not just regions of curved spacetime with event horizons and singularities. They're quantum systems with temperature and entropy, with information content and complex correlations with the rest of the universe. They're laboratories for testing our theories at their limits, places where general relativity and quantum mechanics collide and demand reconciliation. And this brings us back, once again, to our original question. What's on the other side of a black hole? Maybe the question itself needs refining. Maybe there isn't a simple other side in the sense of another location in space. Maybe the other side is a different time, the distant future when the black hole has evaporated. Maybe it's a different quantum state, the complex information encoded in Hawking radiation. Maybe it's another universe, connected through quantum correlations we don't yet fully understand. Or maybe the question reveals a gap in our understanding, a place where our current concepts of space, time, and information are inadequate. Maybe black holes are telling us that reality is fundamentally different from how we imagine it, that the universe has layers and structures we haven't yet conceived. This wouldn't be the first time physics has discovered that reality was stranger than expected. It probably won't be the last. Let's rest here, at this intersection of quantum mechanics, thermodynamics, and information theory. We've journeyed through Hawking radiation, through the slow evaporation of black holes, through the paradox of where information goes, and the various proposed resolutions. We've seen how what seemed like a simple question, what's on the other side, opens into profound mysteries about the nature of reality itself. The journey continues, though, because there are still more angles to explore, more ways of thinking about black holes and the mysteries they contain. Now we venture into territory where the strange becomes stranger still, where connections between distant parts of the universe become woven into the very fabric of quantum mechanics, and where wormholes might be intimately related to one of quantum physics' most mysterious phenomena. This is the realm of quantum entanglement, and a remarkable conjecture that attempts to unite it with Einstein's spacetime bridges. Let's approach this slowly, gently, letting the ideas unfold like flower petals opening to the morning light. Quantum entanglement is one of those phenomena that seems to violate our everyday intuitions about how the universe works. It was first described theoretically by Erwin Schrödinger in 1935. The same year, Einstein and Rosen proposed their wormhole solution, actually. And it remains one of the most puzzling aspects of quantum mechanics even today, nearly a century later. Here's the basic idea, stated simply. Two particles can become entangled in such a way that their quantum states are correlated, no matter how far apart they are. Measure a property of one particle, and you instantly know the corresponding property of the other, even if it's on the opposite side of the universe. They remain connected, not through any physical medium or signal traveling between them, but through their shared quantum state. Einstein famously called this spooky action at a distance, and wasn't happy about it. It seemed to violate the principle that nothing can travel faster than light, the principle that the universe is local, that what happens here shouldn't instantly affect something far away. Yet experiments over the past few decades have definitively confirmed that entanglement is real. Particles genuinely are connected in ways that transcend space, exhibiting correlations that can't be explained by any hidden variables or local hidden information. Let's think about what entanglement actually means and how it differs from our ordinary experience. Imagine two coins that become entangled. They're separated, one sent to Tokyo and one to Sydney. These aren't ordinary coins. They're quantum coins, existing in a superposition of heads and tails simultaneously until measured. When someone in Tokyo flips their coin and sees heads, they instantly know that someone in Sydney will see tails if they flip their coin. The outcomes are perfectly correlated, opposite to each other. But here's the crucial part. Neither person can control what result they get. The person in Tokyo gets a random result, heads or tails with equal probability. Same with Sydney. The correlation only becomes apparent when they compare their results. And because the outcomes are random from each person's perspective, you can't use entanglement to send faster-than-light messages. No information travels between the particles. They're simply correlated in a way that quantum mechanics allows, but our classical intuitions forbid. This is already peculiar and fascinating. But now let's consider how entanglement might relate to spacetime itself, to the geometry of the universe. This is where Juan Maldacena and Leonard Suskind's ER EPR conjecture enters the picture. ER stands for Einstein-Rosen Bridge, the wormhole solution we discussed earlier. EPR stands for Einstein-Podolsky-Rosen, referring to the famous 1935 paper on quantum entanglement. Maldacena and Suskind proposed in 2013 that these two seemingly unrelated phenomena might actually be the same thing, viewed from different perspectives or at different scales. The conjecture states, an Einstein-Rosen bridge, wormhole, is equivalent to Einstein-Podolsky-Rosen entanglement, quantum correlations. In other words, whenever two regions of spacetime are quantum entangled, they're connected by a microscopic wormhole. Conversely, whenever a wormhole exists, the two regions at its mouths are quantum entangled. This is a profound and elegant idea, suggesting a deep connection between the geometry of spacetime and the correlations of quantum mechanics. It hints that spacetime itself, the structure of the universe, the distances between places, might emerge from quantum entanglement. If this is true, then wormholes aren't separate from quantum mechanics. They're a manifestation of it. Let's think about what this might mean. Consider two particles that are quantum entangled. According to ER EPR, they're connected by a microscopic wormhole, a tiny tunnel through spacetime linking them. This tunnel is far too small to traverse. It's at the Planck scale, the smallest meaningful scale in physics, but it's there nonetheless. The wormhole is the physical substrate of the entanglement. If this conjecture is correct, it suggests that entanglement and connectivity in spacetime are fundamentally the same phenomenon. What we perceive as particles being far apart is only approximate. At the deepest level, they're connected by these quantum bridges. The spacetime geometry we experience at everyday scales might emerge from a vast network of entangled qubits, quantum bits of information, each pair connected by a wormhole. This connects to something called the holographic principle, which we mentioned briefly earlier. The holographic principle suggests that all the information in a volume of space can be encoded on the boundary of that volume, like a three-dimensional image encoded in a two-dimensional hologram. ER-EPR provides a specific mechanism for how this could work. Quantum entanglement at the boundary creates the spacetime geometry in the interior through wormholes, linking entangled pairs. Now you might be wondering what this has to do with our original question. What's on the other side of a black hole? Here's where it gets interesting. If ER-EPR is correct, then the interior of a black hole, the region beyond the event horizon, might not be a separate, isolated realm, but rather a quantum state entangled with the exterior. The other side might be, in a sense, right here, woven into the quantum information outside the event horizon. A black hole's event horizon would be a boundary between two regions of spacetime connected by quantum entanglement and wormholes. Matter and energy falling into the black hole would create entanglement with the Hawking radiation escaping outward. The information that seemed to be lost, swallowed by the black hole, would actually be preserved in quantum correlations, accessible in principle to someone analyzing the Hawking radiation carefully. This is a potential resolution to the information paradox we discussed earlier. The information isn't destroyed, it's entangled with the exterior of the black hole through a network of microscopic wormholes. As the black hole evaporates, these wormholes gradually release the information encoded in the Hawking radiation. The other side of the black hole isn't a place you could travel to, but it's still connected, still part of the same quantum system. Let's pause and reflect on this for a moment. We've moved from quantum entanglement, pairs of particles mysteriously correlated across space, to wormholes connecting those particles, to the emergence of spacetime geometry from entanglement, to a potential resolution of the black hole information paradox. Each step follows logically from the previous, yet the conclusion is so strange, so different from our everyday understanding, that it's easy to feel dizzy. Take a breath. Feel how your body rests in the chair or bed supporting you. that physical sensation, that experience locality, still works the way you expect at everyday scales. The ideas we're exploring are about the deepest, most microscopic structures of reality, scales so small they're almost impossible to access experimentally. Our everyday experience remains valid, even if the ultimate foundation of reality is more subtle and interconnected than we imagine. The ER EPR conjecture is not proven. It's a theoretical speculation, an attempt to unify aspects of quantum mechanics with space-time geometry. Different physicists have different levels of confidence in it. Some view it as a promising direction for understanding quantum gravity. Others think it's too speculative, that we need more direct experimental evidence before taking it seriously. The research is ongoing, with new papers exploring different aspects of the conjecture, testing its implications, and seeing where it leads. One of the interesting implications of ER EPR is that if it's true, then entanglement is not just a quantum phenomenon to be understood in isolation. It's not a weird quirk of particles that sometimes behave in correlated ways. Instead, it's the fundamental mechanism by which the universe is structured, by which distances are defined, by which space-time emerges. The geometry of the universe would be built from entanglement, with wormholes being the physical substrate of quantum correlations. This has profound implications for how we think about information and connectivity in the universe. If space-time itself is emergent, arising from quantum entanglement, then what's truly fundamental is information, not space and time. Different ways of organizing information, different patterns of entanglement, would give rise to different space-time geometries. A universe with more entanglement, with richer connections between quantum systems, would have a different space-time structure than one with less entanglement. This brings us to a fascinating thought experiment. Could you change the structure of space-time by controlling entanglement? If entanglement creates wormholes, which in turn creates space-time geometry, then manipulating entanglement might allow you to create or destroy wormholes, effectively reshaping space. This is wildly speculative, far beyond anything we could currently achieve, but it represents the kind of conceptual leap that ER EPR enables, connecting quantum information theory to the geometry of space-time in intimate ways. There are also connections between ER EPR and black hole thermodynamics. We mentioned earlier that black holes have entropy, a thermodynamic quantity related to the number of ways you can rearrange their internal structure without changing their external properties. Bekenstein and Hawking showed that a black hole's entropy is proportional to the area of its event horizon, not its volume. Another surprising result suggesting that information is encoded on surfaces rather than in volumes. If ER EPR is correct, this makes sense. The information in a black hole's interior would be encoded in quantum entanglement between the interior and the exterior, and according to ER EPR, this entanglement is mediated by wormholes concentrated on the boundary between the two regions. The event horizon would be precisely the place where the most intense entanglement occurs, creating the most wormholes and thus the most information density. The entropy being proportional to area rather than volume would follow naturally. Let's think about what this picture suggests for the other side of a black hole. If the interior and exterior are connected by entangled wormholes, then there isn't really a separate other side in the classical sense. There's a region you can't travel to and can't directly observe. That much is still true, because the event horizon still exists and still presents an absolute barrier. But it's not completely disconnected. Information from the interior is encoded in the exterior through entanglement. The other side is woven into this side through quantum correlations. This is a subtle but profound shift in perspective. Instead of imagining the other side of a black hole as a distant realm, inaccessible but existing in parallel, we might think of it as distributed throughout the exterior region, encoded in the quantum state of particles and fields around the black hole. The information that fell in is still there, just scrambled, hidden in correlations that require sophisticated analysis to decode. Some researchers have explored what this means for the holographic principle more deeply. If spacetime emerges from entanglement, and if the event horizon of a black hole represents a boundary where entanglement transitions from high to low, then the black hole's interior emerges from the entanglement just inside the horizon, while the exterior emerges from entanglement just outside. The two regions are connected by wormholes, but these wormholes traverse the event horizon itself, creating a subtle topology where the interior and exterior remain linked, even though they're causally disconnected. This might explain why information falling into a black hole isn't lost, but rather becomes entangled with the exterior. The information doesn't travel outward, that would violate causality, but it does become correlated with the exterior through entanglement. When Hawking radiation is emitted, it carries these correlations outward. Over the eons, as the black hole evaporates completely, all the information is released, encoded in the pattern of radiation. Again, let's pause and breathe. We've explored deep and abstract territory, quantum entanglement as the foundation of spacetime, wormholes as physical manifestations of entanglement, black hole interiors and exteriors as different regions of an entangled quantum state connected by microscopic bridges. These ideas are simultaneously beautiful and bewildering, elegant and mind-bending. It's important to emphasize again that ER EPR is a conjecture, not an established fact. It hasn't been proven, and it may ultimately turn out to be wrong or incomplete. But it represents the kind of thinking that modern theoretical physics is doing about black holes and quantum gravity. It's an attempt to answer fundamental questions about reality. What's space? What's time? What's information? By seeking connections between different areas of physics and exploring what those connections imply. The journey toward understanding black holes, toward answering what's on the other side of an event horizon, is a journey through increasingly abstract and subtle layers of reality. We've started with observable phenomena, black holes in the sky, their shadows captured by the Event Horizon Telescope. We've moved through theoretical physics, Einstein's equations, quantum mechanics, Hawking radiation, and now we're in the realm of speculative research at the very frontier, where mathematics and philosophy intertwine, where the greatest minds in physics are still debating and exploring. What connects all these layers is a deep principle. Nothing is truly lost, nothing is truly isolated. Information persists, transformed but not destroyed. Regions of space that seem separate are connected by subtle channels. The universe is more unified, more interconnected than our everyday experience suggests. These principles appear again and again in different guises as we probe deeper into reality. Let's continue our gentle journey, moving towards synthesis and reflection, toward bringing together the various threads we've woven and asking what they tell us about the fundamental nature of the cosmos and our place within it. We've spent considerable time exploring what might exist beyond the event horizon, what might lie on the other side of a black hole. But there's a deeper question we should explore more fully. What exists at the very center, at the singularity itself? Or rather, what might exist there if the singularity, that point of infinite density predicted by classical general relativity, isn't actually real? This is where modern theoretical physics becomes truly speculative, truly imaginative, because we're now asking about physics at scales where our current theories break down completely. We're asking about the Planck scale, that incredibly tiny distance, about 10 to 35 meters, or a billion billionths of a meter, where quantum gravity effects become dominant, and both general relativity and quantum mechanics are important simultaneously. Classical general relativity predicts that at the singularity, space-time curvature becomes infinite. Density becomes infinite. All the matter that ever fell into the black hole is compressed into a single point of infinite density. But infinities in physics are usually warning signs. They suggest that the theory being used is incomplete, that it's being applied beyond its range of validity. The singularity is almost certainly where this happens with black holes. So what might actually exist at the center of a black hole if we had a complete theory of quantum gravity? There are several intriguing possibilities, each emerging from different approaches to reconciling quantum mechanics with general relativity. Let's explore them gently, one at a time. One possibility comes from loop quantum gravity, a theory that attempts to quantize spacetime itself, treating space and time as woven from discrete quantum loops rather than being smooth and continuous. In loop quantum gravity, spacetime has a granular structure at the Planck scale. It's quantized, made of indivisible units, much like ordinary matter is made of atoms. In this framework, a black hole doesn't have a true singularity at its center. Instead, when matter collapses to the Planck scale density, when everything is compressed into a volume about the size of a Planck length, something remarkable happens. The quantum geometry of spacetime can't be further compressed. It reaches a kind of saturation point where quantum effects prevent further collapse. What happens next depends on the details of the theory, but many versions suggest that the collapse reverses. The matter bounces, begins expanding again, creating a white hole-like region that eventually spews the matter back out, though not necessarily in the same direction or the same time that it came in. The singularity is replaced by a quantum bounce, a brief interval where spacetime undergoes wild, quantum fluctuations, but remains finite and regular. This scenario is remarkable because it would mean that information falling into a black hole isn't destroyed. It gets crushed to Planck scale densities, reverses through a quantum bounce, and eventually emerges on the other side, or in another time, or in another universe, depending on exactly how the geometry works out. The other side of a black hole might be the time after the quantum bounce, when the reversed collapse becomes an expansion. Another intriguing possibility comes from certain versions of string theory, where spacetime itself is not fundamental, but emerges from more basic entities, vibrating strings or higher dimensional branes. In string theory, infinities that appear in ordinary quantum field theory often cancel out, or are replaced by finite values once you account for string effects. The singularity of a black hole might similarly be resolved by string theory, replaced by a stringy object of finite extent. One specific proposal involves fuzzballs, a concept developed by physicist Samir Mathur. In this picture, the singularity is replaced by a string-scale object that's fundamentally fuzzy and quantum, not a sharp point. The black hole's interior is filled with excitations of the fundamental string, creating a dense but finite structure. The information in the black hole would be encoded in the state of these strings, preserved rather than lost. The fuzzball picture also suggests an interesting answer to our question about what's on the other side of a black hole. There might not be a classical other side at all. The interior of the black hole would be a quantum region so different from classical spacetime that the notion of inside and outside, other side, even space, might not apply. You can't meaningfully ask what's beyond a fuzzball, because the concept of space and geometry breaks down at those scales. Yet another approach comes from more recent developments in quantum gravity research. Some physicists have proposed that the information falling into a black hole might be stored in a quantum state on the event horizon itself, the holographic principle manifesting concretely. The interior of the black hole, in this view, isn't really a separate space, but rather a holographic projection or representation of the quantum state on the boundary. This is hard to visualize because our intuitions are built for three-dimensional space, and holography involves encoding three-dimensional information on a two-dimensional surface. But imagine if the entire three-dimensional interior of a black hole was actually the holographic projection of a two-dimensional quantum system living on the event horizon. The other side would be right there, on the boundary, woven into the quantum bits that make up the horizon state. Some researchers have explored even more radical possibilities. What if the singularity is replaced by a connection to another universe entirely? What if the Big Crunch, if our universe eventually stops expanding and begins contracting, is what we'd see if we could observe the other side of a black hole that someone else created in their universe. This is the cosmological bounce scenario we mentioned earlier, where the Big Bang and Big Crunch of different universes might be connected through black holes. These ideas remain speculative, waiting for the development of a complete theory of quantum gravity to be confirmed or refuted. But they share a common theme. The classical singularity, that point of infinite density and infinite curvature, is probably not real. It's a placeholder, a mathematical abstraction that breaks down when quantum effects are included. Replace it with something else, a quantum bounce, stringy fuzz, holographic encoding, a connection to another universe, and you get a more coherent picture. Let's pause here and think about what these alternatives to singularities mean for our understanding of black holes and what might lie beyond their event horizons. They all suggest that the event horizon isn't as absolute, as final as we once thought. If the singularity is replaced by something else, something that might allow information to escape, or time to reverse, or connections to other regions of reality, then the black hole becomes less of a trap and more of a transformation. Information still can't escape through the event horizon in the classical sense. You can't jump into a black hole and come back out. But the information itself, the quantum state describing you, might be transformed, might bounce at the Planck scale, and re-emerge in some form. It wouldn't be you, not in any meaningful sense, but the information would be preserved. This connects beautifully with Hawking's eventual acceptance that information is preserved in black holes, even if the exact mechanism remains unclear. There's something almost poetic about these possibilities. They suggest that black holes, far from being cosmic vacuum cleaners that destroy everything they touch, might be something more like cosmic recyclers. Matter falls in, gets processed at extreme densities, and somehow, through mechanisms we're still working to understand, gets transformed and redirected back into the universe in some form. One of the fascinating aspects of these quantum gravity proposals is that they're starting to make contact with observation, however tentatively. Some versions of loop quantum gravity make specific predictions about how black hole evaporation might proceed at late times, predictions that in principle could be tested if we ever detected a primordial black hole evaporating. String theory makes predictions about the spectrum of black hole oscillations, the frequencies at which they ring when perturbed, that might be testable through gravitational wave observations. The Event Horizon Telescope, which gave us the first images of black hole shadows, is also beginning to constrain these theories. If a black hole's interior had anomalous properties, if it were a fuzzball, or if it had some other exotic structure, it might affect how light orbits at the photon ring, subtly changing the appearance of the shadow. By comparing observations to theoretical predictions in increasing detail, we can gradually rule out different possibilities. This is how science progresses at the frontier, by proposing multiple theories, working out their detailed predictions, and then seeking observations that distinguish between them. We're in the phase of proposing multiple theories, loop quantum gravity, string theory, and various hybrid approaches, all offering different pictures of what replaces the singularity. As observations improve, as our measurements become more precise, and our coverage of different types of black holes more complete, we'll gradually move toward determining which theory, or which aspects of multiple theories, best describes reality. Let's also think about what these alternatives to singularities mean philosophically, beyond the technical details. Classical general relativity predicts that space and time reach a boundary at the singularity, where the equations become undefined. This is a hard boundary, an edge to the universe, a place where our normal concepts completely fail. But if quantum gravity replaces the singularity with something else, a bounce, a fuzzy region, a holographic encoding, then there might not be such hard boundaries. Space and time might extend, transform, or connect rather than terminating. The universe might be seamlessly woven together through these quantum structures, with regions that seem completely separate in classical geometry actually being connected through quantum entanglement, or subtle topological features we can't see directly. This connects to a broader theme in modern physics, the idea that separation and boundaries might be illusions, useful approximations that work at classical scales but break down at quantum scales. Particles that seem distinct can be entangled, sharing quantum states. Regions that seem disconnected can be joined by wormholes. The universe that appears to us as a collection of separate objects, stars, planets, black holes, you and me, might fundamentally be a unified quantum whole, with boundaries and distinctions emerging from how we coarse-grain or approximate the deeper reality. This isn't just idle speculation. These ideas have genuine mathematical content and are being actively researched by physicists at leading institutions around the world. They represent serious attempts to understand the deep structure of reality, to reconcile the two most successful theories we've ever developed, general relativity and quantum mechanics, and to figure out what's really going on inside black holes. As we continue to improve our observations of black holes, as we push gravitational wave astronomy to new limits, as we develop new theoretical frameworks and computational methods, we're gradually assembling a clearer picture. The fog that surrounds black holes' interiors is slowly lifting, not all at once but layer by layer, revealing structure and meaning beneath what once seemed like absolute darkness. The question, what's on the other side of a black hole, is thus not just a question about a distant cosmic phenomenon. It's a window into the deepest questions about space, time, information, and the fundamental nature of reality itself. The answer, whatever it turns out to be, will reshape how we understand the universe and our place within it. Let's rest here, contemplating these alternatives to singularities, these different ways that quantum gravity might resolve what classical relativity can't. The images shift, now a bouncing quantum geometry, now a fuzzball of strings, now a holographic horizon. None is certain. All are possible. Each opens different doors to understanding. The universe holds on to its secrets, but we're learning to ask better questions. Now let's explore one of the most imaginative and profound ideas to emerge from theoretical cosmology and quantum gravity: the possibility that black holes might give birth to universes, not metaphorically, but literally, that the collapse of matter into a black hole might create a new universe that branches off from our own, growing and evolving in its own space-time separate from ours. This idea might sound like pure science fiction, like something conjured from imagination rather than derived from serious physics. Yet it emerges from rigorous theoretical work, from attempts to reconcile general relativity with quantum mechanics, and from thinking carefully about what happens when quantum effects become important near a black hole's singularity. It represents the kind of bold speculation that sometimes points the way toward deeper truths, even when those truths remain beyond our current ability to verify. Let's begin by thinking about what a universe is, at least in the context of modern cosmology. Our universe is the collection of all space and time and matter and energy that we can in principle interact with. But modern cosmology has expanded this picture considerably. We now seriously consider the possibility of a multiverse, multiple universes, each with its own space and time, perhaps with different physical laws or different initial conditions. These different universes wouldn't necessarily be stacked together like pages in a book, accessible from one another through spatial travel. They might be completely separate, with their own space-time continua, only connected through subtle quantum correlations, or perhaps through gravity that operates across higher dimensions. They might be parallel, coexisting, or sequential, with one universe preceding another in some meta-time outside both. If multiple universes exist, the question naturally arises: how do they come into being? What creates a new universe? And here's where black holes enter the picture in a fascinating way. When you work through the mathematics carefully, accounting for quantum effects near the singularity, some scenarios suggest that a black hole's interior might not be a connected region of our spacetime, but rather the beginning of a separate spacetime, a baby universe being born. The theoretical physicist Lee Smolin developed this idea extensively in the 1990s, creating what he called cosmic natural selection. In Smolin's picture, universes produce black holes, and black holes give birth to baby universes. Each baby universe inherits slightly modified physical laws from its parent. The fundamental constants and coupling strengths get slightly randomized each time a universe spawns a new generation. In this view, universes evolve and reproduce, much like organisms in biology. Universes that are good at producing black holes, massive stars that collapse, supermassive black holes at galactic centers, produce many offspring. Universes that are poor at making black holes produce few or none. Over many generations, the population of universes becomes dominated by those that are efficient black hole producers. And here's the remarkable implication. The physical laws of our universe, with the particular values of constants we observe, might have been selected by this cosmic evolution to be conducive to black hole production. This is not proven science. It's speculative cosmology existing at the boundary between physics and philosophy. But it's a serious proposal developed by serious physicists and explored in numerous papers and books. It represents an attempt to answer the deep question of why our universe has the properties it does, why the fundamental constants have the values they have. Questions that otherwise seem to have no scientific answers. Let's think carefully about what this scenario suggests for what's on the other side of a black hole. If a black hole's interior truly is a separate universe, then the other side is quite literally another cosmos, not another location in space, but another entire universe with its own space and time, its own matter and energy, perhaps its own observers contemplating their cosmos just as we contemplate ours. The event horizon would represent the boundary between universes, the place where one spacetime ends and another begins. Matter falling into a black hole in our universe isn't being destroyed or crushed into a singularity. It's passing through a kind of cosmic portal, entering a new universe where it becomes the seeds of structure and complexity. You couldn't travel to the other side and return because the other side is governed by its own time and space. It's not spatially adjacent to ours. This scenario raises profound questions. If black holes spawn universes, how many universes exist? The answer could be astronomical, literally. Every black hole in every universe produces more universes. The structure branches infinitely, a vast tree of cosmos, each one descended from black holes in its parent generation. We live in one leaf of this infinite tree, ourselves descendants of black holes from some earlier generation, potentially parents of universes through the black holes we contain. How would this actually work, mechanically? The mathematics suggests that when quantum effects near the singularity are properly accounted for, the singularity might be replaced by a bounce or a transition. The collapsing spacetime doesn't crunch to infinite density, but instead curves back around, expanding again, but not back into the original universe. Instead, it opens into a new spacetime, a new universe that's causally disconnected from the one the black hole formed in. The new universe would start in conditions somewhat similar to the Big Bang of our own universe, hot, dense, filled with radiation and particles. It would then evolve according to physical laws, developing structure, forming stars and galaxies, and eventually black holes of its own, which would spawn yet another generation of universes. Each generation adds layers to the multiverse, each universe contributing to the total diversity of cosmos. One of the beautiful aspects of this picture is that it provides a potential solution to what cosmologists call the fine-tuning problem. The physical constants of our universe, the strength of gravity, the masses of fundamental particles, the strength of the strong and weak nuclear forces, all seem to be precisely tuned to allow for the existence of stars, planets, and life. If these constants were different by even small amounts, the universe would be sterile, incapable of producing complexity. Why are the constants fine-tuned? One answer is pure chance. We happen to find ourselves in a universe that's fine-tuned, because if it weren't, we wouldn't be here to observe it. This is the anthropic principle. But another answer, suggested by cosmic natural selection, is that the constants have been selected by evolution to be conducive to black hole production, since black holes are good at making universes, and since the ability to make black holes depends on having the right physical constants. Universes good at producing black holes proliferate. Our universe is fine-tuned for black hole production, and this fine-tuning happens to make it also fine-tuned for the emergence of complexity and life. It's an elegant idea, and it connects the microscopic physics of black holes to the larger-scale structure of reality. It suggests that even our existence, the fact that we're here, contemplating the universe, is connected to black holes and the universes they spawn. Let's pause here and breathe. This idea that black holes create universes, that we might be inside a baby universe created by a black hole in some parent cosmos, that countless universes branch off infinitely from black holes. This is wild territory, strange and wondrous. It's the kind of idea that challenges our intuitions about what's possible, what's real, what constitutes a universe. The honest truth is that we have no observational evidence for baby universes spawned by black holes. We can't see another universe budding off from a black hole. We can't detect the baby universes directly. We have no way to verify whether cosmic natural selection is real or merely an elegant mathematical possibility. This is where theoretical physics reaches the limits of what it can currently accomplish, where imagination and mathematics intertwine, and where certainty gives way to possibility. Yet there's value in exploring such ideas, even when we can't verify them. They stretch our thinking. They challenge us to consider possibilities beyond our everyday experience and conventional assumptions. They connect different areas of physics, cosmology, quantum mechanics, general relativity, in novel ways. And they sometimes contain seeds of insight that lead, eventually, to testable predictions and new understanding. Some physicists have suggested that if baby universes are real, there might be ways to detect them indirectly. For instance, if a baby universe bud off from our spacetime while it was still connected, it might leave behind a small defect or scar in the geometry of spacetime, something that might be detectable through the precise measurement of gravitational fields or through anomalies in the cosmic microwave background radiation. Others have explored what it would mean if our universe is itself a baby universe, born from a black hole in some parent universe. In this scenario, the Big Bang wasn't the beginning of everything, but rather a transition from one universe to another. The Big Bang singularity would be replaced by a kind of quantum bounce or transition, consistent with some approaches to quantum gravity. Our observable universe, the portion of space and time we can see, would be just the interior of a black hole formed in some larger parent universe. This is a perspective shift that's almost impossible to fully grasp. We think of ourselves as inhabiting a vast universe billions of light years across. Yet in this picture, our entire universe might be the interior of a black hole that formed in some larger cosmos. The boundaries of our observable universe, the cosmic horizon beyond which we can't see, might correspond to the event horizon of that black hole, as seen from the outside. What would this mean? It would mean that nothing in our universe can influence anything outside our cosmic horizon, because beyond that horizon is outside the black hole's event horizon, causally disconnected from us. It would explain the horizon we observe. It's not an accident or an artifact of our finite light travel distance, but a genuine boundary of our universe. And it would suggest that someone in the parent universe, if they existed, could in principle calculate what happens inside our universe just from knowing the properties of the black hole that gave birth to us. This connects to the holographic principle again. If our universe is the interior of a black hole in a larger universe, then the information in our universe is encoded on the event horizon, a two-dimensional surface of the parent universe. Everything that happens to us, all of cosmic history, all of matter and energy and thought, is in some sense a holographic projection from the parent universe's boundary. It's a dizzying thought, collapsing the distinction between inside and outside, between our universe and something larger. Again, we must emphasize, this is speculative theoretical work, not confirmed science. But it's the kind of speculation that emerges when you take quantum gravity seriously, when you follow the mathematics to its conclusions and see where it leads. And that's valuable because it expands the range of possibilities we consider, the hypotheses we're willing to take seriously enough to explore. Let's think about what baby universes would mean for our original question. What's on the other side of a black hole? In this picture, the answer is clear and profound. Another universe. Not another place, but another cosmos with its own space and time. The other side is a universe being born, growing from a singularity that's actually a point of connection between universes, a cosmic umbilical cord. And if our universe is itself a baby universe, born from a black hole in some parent cosmos, then asking what's on the other side of our universe's black holes is asking about us, in a sense. We're on the other side of someone else's black hole. We're the baby universe that resulted from their black hole's collapse. We're a universe alive inside a cosmic structure formed in a larger reality. This perspective suggests a kind of cosmic genealogy, a family tree of universes extending infinitely into the past, universes that birthed ours, and infinitely into the future, universes born from our black holes. We're nodes in a vast network, connected by black holes and entanglement, part of a multiverse tapestry that unfolds across scales and timeframes almost impossible to comprehend. Whether this is how reality actually works remains to be determined. Future developments in quantum gravity, new observational techniques, or unexpected theoretical breakthroughs might provide evidence to support, refute, or fundamentally reshape these ideas. But for now, the possibility of baby universes remains one of the most profound and fascinating suggestions for what might exist on the other side of a black hole's event horizon. Let's rest here, contemplating these infinite branches of cosmos, these universes spawning universes through black holes, this vision of reality as endlessly fertile and creative at its deepest levels. The image is strange and wonderful, unsettling and magnificent. It invites us to expand our sense of what's possible, what's real, and how vast the cosmos might truly be. We've traveled through theoretical landscapes both beautiful and bewildering, wormholes and white holes, quantum entanglement and baby universes, alternatives to singularities and speculative cosmologies. But now let's gently return to something more tangible, more grounded in observable reality. Let's explore what clues we have today about black holes' true nature, what observations might help us distinguish between competing theories, and what future discoveries might illuminate the mysteries we've been pondering. The most direct observational approach we have so far is gravitational wave astronomy, the detection of ripples in spacetime produced by massive accelerating objects. When two black holes orbit each other and eventually merge, they create gravitational waves that radiate outward at the speed of light. The LIGO and Virgo observatories have detected dozens of these mergers since 2015, and each detection provides valuable information about black holes' properties and behavior. What's remarkable is how precisely these observations match Einstein's predictions. When two black holes merge, general relativity predicts that they'll spiral together, merge into a single larger black hole, and then ring down, oscillate like a struck bell, emitting gravitational waves at specific frequencies determined by the final black hole's mass and spin. The LIGO and Virgo detections have confirmed these predictions in exquisite detail. But here's what's particularly interesting for our question about what's inside black holes. If black holes have exotic interiors, if they contain wormholes, or if they're fuzzy balls rather than smooth event horizons, or if they contain any structure significantly different from what Einstein's equations predict. These differences might show up in the gravitational wave signals. The oscillation frequencies after a merger are extremely sensitive to the black hole's properties. They depend on the metric, the mathematical description of spacetime geometry, near the event horizon. If the spacetime geometry is different from Einstein's prediction, if there's something unusual lurking just inside the event horizon, the ring-down frequencies would be different. By measuring these frequencies with higher and higher precision, we can test whether classical general relativity is exactly right, or whether quantum corrections and other modifications become important. So far, every measurement supports classical general relativity, but the precision of current observations is limited, and future detectors will be even more sensitive. The Einstein telescope, proposed for Europe, and the Cosmic Explorer, proposed for the United States, will be able to measure gravitational wave signals about 1,000 times more precisely than current detectors. These upgrades might reveal subtle deviations from general relativity's predictions, hints of the quantum gravity effects that become important at Planck scales. Another observational approach involves X-ray observations of black holes. Material in accretion disks around black holes gets heated to millions of degrees and emits X-rays that we can detect from Earth. By carefully analyzing the spectrum, the distribution of X-ray intensities at different energies, astronomers can infer properties of the spacetime around the black hole. One particularly useful feature is the iron fluorescence line, a characteristic X-ray emission from iron atoms in the accretion disk that's been energized by X-rays from hotter regions closer to the black hole. The shape and width of this line tells us about the black hole's spin, how fast it's rotating. Different spin values produce different distortions of the iron line due to relativistic effects and frame dragging. More importantly, if black holes had exotic interiors, or if the event horizon had unusual properties, these might affect how material orbits and radiates, subtly changing the X-ray spectra we observe. By comparing observations to theoretical predictions, we can constrain how exotic black hole interiors can be. So far, the observations are consistent with classical general relativity, but again, precision continues to improve. The Event Horizon Telescope observations we discussed earlier provide yet another window into black holes. The size and shape of the black hole shadow, the brightness and symmetry of the photon ring, these encode information about the space-time geometry near the event horizon. As the Event Horizon Telescope adds more telescopes to its network and achieves higher resolution, it will be able to detect finer details in these images. One particularly intriguing possibility is that future Event Horizon Telescope observations might detect multiple images or echoes, light that has orbited the black hole multiple times before escaping. These echoes would appear as fainter rings inside or outside the main photon ring, and they would be extremely sensitive to the exact geometry of space-time near the black hole. If the geometry is slightly different from Einstein's prediction, the echo patterns would be different. Detecting echoes could reveal whether something unusual is lurking inside. There's also considerable interest in the possibility of detecting primordial black holes. Black holes formed in the very early universe, not from stellar collapse, but from density fluctuations in the primordial plasma. These would have a range of masses, and if they exist, some of them would be evaporating right now through Hawking radiation. The observational signature would be gamma rays, high-energy photons produced as the black holes evaporate. Searches for these gamma-ray bursts have so far come up empty, which places limits on how many primordial black holes can exist. But the searches continue, and if a primordial black hole were detected, it would be revolutionary. Direct evidence of Hawking radiation and a window into physics at tiny scales. There's also fascinating work being done on black hole thermodynamics and the connections to quantum information. Some researchers are exploring whether the event horizon might have structure at quantum scales, quantum fluctuations that might be detectable through their effects on particle trajectories or on light paths. If the horizon is more subtle and structured than a simple smooth surface, this might show up in very precise gravitational or electromagnetic measurements. One intriguing proposal involves using the Sun or Jupiter as a gravitational lens to magnify observations of distant black holes or other compact objects. The gravitational lensing naturally amplifies faint signals, potentially allowing us to see details that would otherwise be too small or too dim to observe. This technique, called stellar mass black hole imaging, might eventually allow us to map the structure of spacetime near black holes with unprecedented precision. Another avenue of research involves studying the tidal forces and spacetime curvature near black holes using spacecraft or satellites. Though we can't send anything deliberately into a black hole, we could in principle send a satellite or probe very close to one, with instruments measuring the local spacetime curvature and reporting data back. The extreme tidal forces would be lethal, but robots and remote instruments could potentially survive long enough to make measurements. Such a mission is far beyond our current technology, but it represents a possible future avenue for direct probing of black hole environments. There's also work being done on whether black holes might have an internal structure detectable through quantum entanglement. Some physicists have proposed experiments, though currently only thought experiments, involving quantum information and entanglement that might reveal whether information falling into a black hole is truly scrambled, or whether it leaves some detectable imprint. These experiments would require technologies far beyond what we currently possess, like the ability to create and manipulate entangled quantum states at scales relevant to black holes. But they represent the kind of creative thinking that theoretical physicists engage in, exploring what could in principle be measured if we had the technology. Let's pause here and reflect on the state of black hole science. We have more direct observational data about black holes than ever before in human history. We can image their shadows, detect their mergers, measure their spins and masses, map the radiation from their accretion disks. Yet the deep mysteries remain. We still don't know definitively what's at the center of a black hole, whether the singularity is real or replaced by something else, whether information is preserved or lost, whether there are wormholes or baby universes or any of the other exotic possibilities we've explored. This is partly because the observational signatures of different theories are subtle and require enormous precision to distinguish. It's also because many of the most interesting effects, quantum gravity effects, Planck scale physics, operate at scales far too small, or in regimes far too extreme for us to directly observe with foreseeable technology. Yet science progresses gradually, through accumulation of data and refinement of theories. Every gravitational wave detection, every improved black hole image, every new X-ray or radio observation constrains the possibilities further. Over decades and centuries, the picture will become clearer. Eventually, one theory or set of theories will emerge as best matching reality, though we may always be humbled to discover that reality is stranger and richer than we imagined. There's also the possibility of serendipitous discovery, unexpected observations that force us to revise our thinking entirely. History is full of examples where something unexpected appeared in the data and led to revolutionary insights. A strange pattern in gravitational wave signals, an anomaly in black hole orbits, an unexpected emission from a distant black hole. Any of these could hint at physics beyond current theories. Another productive avenue is theoretical exploration guided by mathematical consistency. Sometimes by carefully working through the logic of various theories, by exploring their implications and looking for internal contradictions or unexpected connections, physicists stumble upon ideas that later prove prescient. The ER EPR conjecture, for instance, wasn't motivated primarily by observation, but by the elegant mathematical relationships between entanglement and wormholes. Whether it's correct remains unclear, but it points toward new ways of thinking about black holes and space-time. There's also considerable interest in numerical simulations, using supercomputers to solve Einstein's equations and related quantum gravity equations in regimes too complex for analytical solution. These simulations can predict what gravitational wave signals or other phenomena should look like under various assumptions about black hole interiors. Then, when real observations come in, they can be compared to the simulations to see which scenario best matches reality. Some particularly ambitious simulations are attempting to model what happens at the moment of black hole formation, when a massive star collapses. These simulations try to incorporate quantum effects, magnetic fields, radiation pressure, and all the other physics relevant to real astrophysical collapse. They might reveal whether classical singularities actually form, or whether quantum effects prevent the density from ever reaching infinite values. Looking further into the future, there are proposals for space-based gravitational wave detectors that would be even more sensitive than Earth-based detectors and could observe different types of black hole mergers. There are also proposals for extremely long baseline radio interferometry arrays that would extend beyond Earth, eventually to space, and potentially even to the Moon, enabling black hole imaging at far higher resolution than the current Event Horizon Telescope. Decades from now, centuries perhaps, we might have black hole movies, not just static images but time-resolved observations showing how material moves and evolves near the event horizon, how jets form and evolve, how magnetic fields interact with the extreme space-time curvature. These movies would be windows into the most violent, most extreme environments in the universe, windows into physics at its limits. There are even more speculative possibilities. Some physicists have wondered whether advanced civilizations might be able to extract energy from black holes through the Penrose process, which theoretically allows you to tap the rotational energy of spinning black holes. If such processes are real and practical, they might leave observational signatures, anomalous energy emissions, or matter trajectories. Searching for these signatures might be a way to detect evidence of advanced technologies using black holes. Or perhaps one day, with sufficiently advanced physics and technology, we might be able to create stable wormholes and use them for traversal or communication. The theoretical work on traversable wormholes suggests that if you could somehow generate exotic matter with negative energy density and shape it into the right configuration, you could stabilize a wormhole and hold it open. An advanced civilization might do this, and the observational signatures of such artificial wormholes might eventually be detectable. Again, this is highly speculative, possibly impossible given physical laws we don't yet fully understand. But it represents the kind of future that modern theoretical physics is willing to entertain, the long-term possibilities that emerge when you take the equations seriously and explore them to their logical conclusions. For now, we continue the patient work of observation and theoretical development, accumulating data, refining theories, gradually pushing back the frontier of ignorance. Black holes remain profoundly mysterious, but they're also becoming increasingly accessible to study. Each year brings new observations, new insights, new questions. The journey continues. Let's rest here, contemplating the future of black hole science, imagining the discoveries that might await us. We've journeyed from theory to observation and back again, from the deepest quantum gravity speculations to the concrete data collected by instruments on Earth and in space. The mystery of what's on the other side of a black hole remains unsolved, but the tools and methods for solving it are gradually being refined and improved. Now, as we approach the gentle conclusion of this journey through black holes and cosmic mysteries, let's weave together the various threads we've explored. Let's step back and ask, what emerges when we consider all these possibilities together? What common themes and insights appear across the different approaches? What might the answer to our original question truly be? We began simply, asking what's on the other side of a black hole. Along the way, we've explored Einstein's curved spacetime, wormholes and white holes, quantum entanglement and information paradoxes, alternatives to singularities, baby universes, and speculative observational approaches to testing these ideas. Each avenue of exploration has offered different answers, different perspectives on the same fundamental question. Let's consider what these different answers have in common. The first and most striking commonality is that in almost every serious theoretical approach, the notion of complete, absolute separation, that what's inside a black hole is totally and forever disconnected from everything outside, doesn't hold up under careful scrutiny. In classical general relativity, inside the event horizon is indeed completely separated from outside. Information and matter can only move inward. Nothing escapes. But when we account for quantum effects through Hawking radiation, suddenly the black hole is connected to the exterior through the particles being emitted. Information that fell in is gradually released back, encoded in the radiation in ways we're still learning to decode. When we consider wormholes and the ER-EPR conjecture, inside and outside are connected by microscopic bridges through spacetime and quantum entanglement. When we consider alternatives to singularities from quantum gravity, we find that the collapse might not terminate in a singularity, but instead reverse or transform, potentially connecting to another region or another universe. When we consider baby universes, the inside isn't just another region of our spacetime, but an entirely separate cosmos. Yet it's still born from a black hole, still causally derived from our universe, still connected through the history of matter and energy. Across all these scenarios, a pattern emerges. Black holes are not absolute voids, not absolute endpoints. They're transformation points, places where matter and energy undergo profound changes. They're connections, whether to quantum states encoded on horizons, to other regions through wormholes, to future states through Hawking evaporation, or to entirely other universes through cosmic spawning. Black holes are the most extreme laboratories where different levels of physics interact. Quantum and classical, microscopic and cosmic. This universe, and potentially others. This suggests a deeper principle at work in nature. Nothing is truly isolated. Everything is connected to everything else through subtle channels we're only beginning to understand. The universe is more unified, more woven together than our everyday experience of separated objects and distinct locations would suggest. Here's another common thread. Information is never truly destroyed. This principle appears across multiple theories and approaches. Hawking radiation, according to modern thinking, preserves information through subtle correlations. Holographic principles suggest information is encoded on boundaries. Quantum gravity approaches suggest that information is preserved through quantum entanglement or through transitions to other states or universes. The deeper the theories go, the more fundamental the principle becomes. The universe conserves information. This isn't just a technical detail, it has profound implications. It suggests that the universe is fundamentally deterministic at some level, even if it appears random or chaotic at other levels. It suggests that reality at its foundation is conservative, preserving all knowledge of what has been, even when transforming it beyond recognition. It suggests that nothing is truly lost, even when matter seems to vanish into a black hole. A third theme that emerges across different approaches is the importance of scales. Black holes look and behave very differently depending on what scale you examine them at. At cosmological scales, they're nodes in a universe-spanning network. At Planck scales, they're quantum objects where geometry itself becomes probabilistic. At intermediate scales, they're classical objects described by general relativity. Understanding black holes requires understanding how these different scales connect and how physics at different scales emerges from or connects to physics at other scales. This scaling perspective suggests something important about the question itself. What's on the other side of a black hole might not have a single answer that's valid at all scales. At classical scales, the answer might be nothing, just the continuing space-time geometry. At quantum scales, the answer might be a foamy network of entangled particles and virtual wormholes. At cosmological scales, the answer might be another universe entirely. The other side is different depending on what scale and what perspective you examine it from. A fourth common theme is the blurring of distinctions that seemed clear at first. The distinction between inside and outside becomes subtle near quantum gravity scales. The distinction between different universes becomes ambiguous if they're connected by wormholes or quantum entanglement. The distinction between space and time becomes unclear inside event horizons, where time becomes spatial in some sense. The distinction between particles and information becomes blurred at quantum scales, where particles are excitations of quantum fields. This progressive blurring of distinctions is characteristic of deep theoretical physics. As we understand nature more deeply, the sharp boundaries and categories we use at everyday scales dissolve into subtler, more nuanced relationships. This doesn't mean our everyday intuitions are wrong. They work fine for everyday scales. It just means that reality is richer and more intricate than those intuitions capture. Now, let's think about what all this means for our original, seemingly simple question. What's on the other side of a black hole? The most honest answer, given everything we've explored, is we don't know yet, and the question itself might need refinement. What we do know is that black holes are not absolute endpoints, not places where information and existence simply cease. Black holes are transformation points, places where matter undergoes changes that are extreme, but not infinite or absolute. Black holes connect regions of space, link different times, possibly bridge different universes. Black holes encode information, preserve it through quantum correlations, even if it's scrambled beyond recognition. The other side of a black hole, in whatever sense that phrase ultimately means, is woven into the structure of the black hole itself and connected to the universe outside through multiple subtle channels. It's not a separate place you could visit, but it's not completely inaccessible either. The information is encoded in the radiation, hidden in quantum correlations, preserved through symmetries and conservation laws that physics demands. If we had to hazard a guess, synthesizing everything we've explored, it might be something like this. On the other side of a black hole's event horizon, classical spacetime as we know it ceases to be a useful description. Instead, at the deepest levels, there's a quantum regime where distinctions between inside and outside, space and time, this universe and others become ambiguous. This quantum regime is connected back to the classical exterior through Hawking radiation and through the quantum entanglement of the horizon with the rest of the universe. If the black hole ever completes its evaporation, if it radiates away all its mass through Hawking radiation, the information that fell in would be released back into the universe, scattered through the radiation in a way that's scrambled but not destroyed. In this sense, the information does emerge on the other side, but not as a coherent return. It's return transformed, integrated into the quantum state of the universe in a way that's consistent with quantum mechanics, but that makes reconstruction of the original state effectively impossible. Alternatively, if quantum gravity introduces something like a bounce at the Planck scale, the collapsed matter might reverse its fall and expand again, creating a white hole or a transition to another universe. In this case, the other side would be the state after the bounce, whether that's a new region of our space-time or a separate cosmos entirely. Or perhaps, if baby universes are real, the other side is literally a new universe, just being born from the collapse, growing according to its own laws of physics, unaware of its parent cosmos. In this view, countless universes are being born all the time from black holes in countless parent universes. We're simultaneously living in a universe and hosting baby universes from our own black holes. The beautiful thing about these different possibilities is that they're not necessarily contradictory. Different aspects might be true simultaneously at different levels of description. Quantum bounces and baby universes might both happen. Information might be both preserved through Hawking radiation and tunneled to another universe. Wormholes might connect regions of space while also connecting different times or different universes. Physics at the frontier often discovers that apparent contradictions resolve when you understand the deeper structure. Things that seemed incompatible at one level become complementary at another. The principle of complementarity, used frequently in quantum mechanics, might apply here too. Black holes might be both isolated traps and connected bridges, both endpoints of spacetime and beginnings of new universes, both classical objects and quantum entities, depending on what aspect you examine and what level of description you use. Here's another thought worth contemplating quietly. The fact that we're asking these questions at all, the fact that we're capable of wondering about the nature of reality and working through complex mathematics to explore possibilities, might itself be part of the answer. If baby universes are real, and if our universe is a baby universe born from a black hole in some parent cosmos, then the fact that we exist and are capable of thought and science is remarkable. We're not just random consequences of physical law. We're the universe becoming conscious of itself, the cosmos exploring its own nature through the emergence of observers. In some versions of quantum gravity and multiverse theory, this kind of self-aware universe with observers capable of questioning reality is actually more likely to exist than universes without observers. The reasoning is subtle, involving quantum effects and the role of measurement in collapsing wave functions. But it suggests that the universe might be organized in ways that favor the emergence of complexity, consciousness, and self-reflection. This takes us from purely physical questions into something approaching philosophy or even the spiritual. It suggests that the universe at its deepest level might not be indifferent and mechanical, but rather organized in ways that support and perhaps encourage the emergence of awareness and knowledge. Whether this is actually true or just a beautiful idea remains to be seen, but it's worth contemplating. Let's also acknowledge the profound humility that black holes teach us. For most of human history, we operated under the assumption that we understood the universe's basic structure. Space was space, time was time, matter was matter. Newton's laws worked. Even Einstein's relativity, revolutionary though it was, seemed to offer a complete picture, at least until singularities appeared and refused to make sense. Black holes revealed that our understanding was incomplete. They showed us that at extreme densities and strong curvatures, reality behaves in ways our intuitions can't grasp. Quantum effects revealed further mysteries. The information paradox showed us that combining quantum mechanics with general relativity produced genuine puzzles with no obvious solution. And at each stage, the universe proved richer, stranger, and more profound than we'd imagined. This should instill in us a kind of epistemic humility, recognition that our current understanding, while powerful and useful, is incomplete. There are likely phenomena and principles we haven't yet discovered, layers of reality we haven't yet conceived. Black holes represent our current frontier of ignorance and exploration. What lies beyond that frontier? What new physics? What new principles? What new ways of understanding reality? Remains to be discovered. Yet this humility doesn't mean we should abandon the search for understanding. If anything, it makes the quest more meaningful. We're exploring a universe vast beyond comprehension, seeking to understand processes and structures at scales and extremes, far beyond everyday experience. The fact that we're still discovering new mysteries, still revising our theories, still being surprised by nature, this is exactly what science should be. Black holes, in this sense, are gifts. They're laboratories of extreme physics, places where we can test the limits of our theories and discover where they break down. They're invitations to think more deeply, more carefully, more creatively. They're reminders that the universe is fundamentally more profound than we typically imagine. As we bring together all the threads we've woven through this gentle exploration, the picture that emerges is one of profound interconnection, subtle conservation, and layered complexity. Black holes are not what they first appeared to be, simple voids into which everything falls and disappears. Instead, they're intricate structures, connection points between different regimes of physics, places where information is transformed but preserved, possibly portals to other universes, or points of cosmic procreation. What's on the other side of a black hole? Perhaps the deepest answer is simply more of the universe, but in a form transformed beyond recognition. More reality, more cosmos, more existence, just hidden behind the event horizon, encoded in quantum states, connected through channels we're learning to map. The other side isn't separate from this side. It's woven into it through subtle channels, visible not directly, but through their effects on the physics we can observe. And that, in its own way, is as wondrous and as beautiful as any specific discovery could be. It's the beginning of understanding, the recognition that there's more to learn. And that ongoing journey of discovery is perhaps the greatest gift the universe offers us. What's on the other side of a black hole? It's the question that brought us here, whispered softly at the beginning, like a curious child wondering about the mysteries that hide beyond the visible horizon. And after wandering through Einstein's curved spacetime, across wormholes and through quantum correlations, past event horizons and toward theoretical singularities, we find ourselves gently circling back to where we began, still wondering, still marveling, still contemplating the most profound mysteries of the cosmos. We've learned so much, you and I, on this quiet journey together. We've discovered that black holes are far more than simple cosmic vacuum cleaners. They're intricate structures woven from space-time itself, places where the rules of physics become strange and beautiful, where multiple theories offer different perspectives on the same reality, all of them containing pieces of truth. We've explored that the event horizon isn't quite as absolute as it first appeared. Hawking radiation connects the interior to the exterior, carrying away energy and possibly information. Quantum entanglement might link the inside and outside through microscopic wormholes. The information falling into a black hole might not be destroyed but rather transformed, scrambled, preserved in ways that obey the deep principles of quantum mechanics. We've learned that asking what's on the other side of a black hole opens into questions about the nature of space, time, information, and the fundamental structure of reality itself. We've pondered the possibility of wormholes, those hypothetical tunnels through space-time that could connect distant regions or different universes. We've considered the elegant mathematics of the Einstein-Rosen Bridge and the intriguing ER EPR conjecture, suggesting that wormholes and quantum entanglement might be aspects of the same phenomenon. We've contemplated white holes, those time-reversed mirrors of black holes that emerge from the equations but seem forbidden by thermodynamics. We've journeyed through the information paradox and the various proposed solutions, each suggesting that the universe preserves what falls into black holes through subtle mechanisms we're still working to understand. We've explored alternatives to singularities, quantum bounces, fuzzballs, holographic horizons, recognizing that the infinities predicted by classical general relativity probably aren't real, that something else emerges when quantum effects are properly included. We've even ventured into the realm of baby universes, considering the possibility that black holes might be cosmic portals to newly born universes, that our own cosmos might be the interior of a black hole formed in some parent universe. These ideas seem wild, yet they emerge from serious theoretical work, from attempts to reconcile quantum mechanics with general relativity in consistent ways. We've examined the observational evidence, the images from the Event Horizon Telescope showing the shadows of black holes, the gravitational wave detections confirming Einstein's predictions with remarkable precision, the X-ray observations revealing properties of black holes' immediate environments. And we've recognized that while our observations are becoming increasingly sophisticated, the deepest mysteries remain hidden behind the event horizon, perhaps forever inaccessible to direct measurement. Most importantly, we've learned that the universe is far more profoundly interconnected than everyday experience suggests. Nothing is truly isolated. Nothing is truly lost. Everything connects to everything else through subtle channels, through gravity and space-time curvature, through quantum entanglement and information encoding, through the conservation laws that govern reality at its deepest levels. The picture that emerges from all our exploration is one of subtle, elaborate connection. The black hole's interior isn't a separate realm, but rather a transformed aspect of the same universe, intimately linked to the exterior through quantum correlations and information flows. The other side isn't a distant location, but rather a state of being, a configuration of reality transformed beyond recognition, but still connected, still part of the same cosmos. Maybe black holes don't have a simple answer to what's on the other side. Maybe the answer is that there are many sides, many perspectives, many ways of understanding what happens when matter reaches the extreme densities and curvatures that only black holes achieve. Maybe the question itself needs refining as our understanding deepens, and maybe that's exactly how it should be. The universe doesn't owe us simple answers, doesn't promise that reality will match our preconceptions. Reality simply is, strange and profound and infinitely richer than we imagine. Perhaps what's most important isn't the specific answer to what's on the other side of a black hole, but rather what exploring this question teaches us about the nature of reality, about the interconnectedness of all things, about the limits and possibilities of our understanding. Black holes are cosmic teachers, showing us where our theories break down and inviting us to think more deeply, more carefully, more creatively. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though, if I was, well, at least you've learned a few things about black holes, event horizons, and the mysteries that lie at the edges of space-time along the way. And if you're already drifting into the gentle twilight between waking and sleep, may your dreams be filled with cosmic visions, photon rings glowing around event horizons, wormholes threading through space-time, universes budding from black holes in some metadimensional garden. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Are you tucked into bed in Singapore at 3 a.m, the city quiet beyond your window, or perhaps relaxing on a couch in Toronto on a quiet evening while the snow gently falls outside? Are you in a library in Sao Paulo, stealing a moment of wonder between the demands of the day? Let me know in the comments and share with our community. It's always such a joy to see this sleepy science community scattered gently across the globe, all of us gazing at the same mysterious universe, all of us contemplating the same profound questions from different corners of the earth. If you found this gentle journey into black holes, event horizons, and cosmic mysteries relaxing or informative, or perhaps both at once, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the cosmos and beyond. More explorations of the universe delivered at the pace of a quiet whisper. More voyages through the wonders of science designed to soothe your mind, even as they stretch your understanding. Whether you stay awake to the very end or drift away somewhere in the middle, thank you for joining me on this journey through black holes and the mysteries of space-time. Thank you for being patient with complex ideas, for letting your mind wander through theoretical landscapes, for contemplating questions that humanity has only recently begun to ask. Sleep well, dream deep, and may your thoughts be filled with gently spiraling accretion disks, softly bending starlight, and the wonder of a universe so profoundly strange and beautiful that even our wildest theories barely scratch the surface of its mysteries. Remember that somewhere in the quantum foam, in the depths of space-time, infinite versions of you are already peacefully asleep, their waves of probability gently collapsing into dreams of cosmic wonder. And perhaps, just perhaps, those versions of you are asking the same questions about black holes from the comfort of their own gentle evenings. You are part of a universe that's far more connected, far more wondrous, far more profound than you might have imagined. You are made of stardust that once orbited massive stars. You contain atoms that have fallen through gravitational fields and been transformed. Your consciousness is a manifestation of the universe becoming aware of itself, contemplating its own nature through the eyes and minds of observers like you. So rest gently. Let go of the questions, at least for now. Your mind has journeyed far tonight, traveled through theoretical landscapes and cosmic mysteries. It deserves to drift now, to float gently down towards sleep, like a feather falling through still air. The universe will still be here tomorrow, full of mysteries and wonders, waiting patiently for you to return to contemplation. But for now, just let yourself rest. Thank you for everything, for your time, your attention, your willingness to wonder, for choosing to spend this evening with me, exploring the cosmos at a gentle pace, for being part of a community that values curiosity, that values beauty, that values the search for understanding even when the answers remain mysterious and elusive. Sleep well, dream softly, and good night.